Hello, and welcome to this quiet hour we share together. There is something happening right now. Even as you rest here, something so gentle and so constant that most of the world sleeps through it entirely. In the hours before dawn, across every blade of grass, every leaf, every surface that faces the open sky, tiny spheres of water are forming, one invisible molecule at a time, gathering silently in the darkness, waiting for the first light to reveal them. This is the world of morning dew, and it is one of the most peaceful processes that nature offers us. You can let your shoulders settle now, if you'd like. There's no need to hold anything tightly here. I know you might be tired. Perhaps the day has asked much of you, or perhaps you simply seek a softer place for your thoughts to wander. Either way, you've arrived somewhere calm. The science we'll explore tonight asks nothing of you except your gentle attention, and even that can drift and return as it pleases. If these journeys bring you comfort, you're welcome to return anytime. There will always be more quiet wonders waiting. Let's begin, then, by stepping outside in our minds, into the coolness just before sunrise, and asking the simplest question: where does dew come from? It begins, as so many things do, with the air itself, the air around us. The air moving gently through the room where you rest now is never truly empty. It holds within it countless molecules of water, invisible and dispersed, floating freely in the space between nitrogen and oxygen. This water exists as vapor, a gas, unbound and light. During the day, warmth keeps these molecules energetic and separate. They drift and tumble through the atmosphere, never settling, never gathering. But as the sun descends and the earth begins to release the heat it has stored, something shifts. The air cools, and with that cooling, the behavior of water vapor begins to change in the most subtle and beautiful way. Every substance, every material in the universe has a relationship with temperature. Water is no exception. When air is warm, it can hold a great deal of water vapor, keeping it suspended, invisible, part of the breath of the world. But as the temperature drops, the capacity of air to hold that vapor decreases. The molecules slow, they lose energy, and at a certain point, a threshold quiet and specific, the vapor can no longer remain a gas. It must transform, it must condense. This threshold is called the dew point, and it is one of the most elegant concepts in all of atmospheric science. The dew point is not a fixed number. It changes with the amount of moisture already in the air. On a humid evening, when the air is thick with invisible water, the dew point is high. The air doesn't need to cool very much before condensation begins. On a dry evening, the dew point is low, and the temperature must drop significantly before dew can form. This is why some mornings glisten with moisture and others remain dry. The dew point is a quiet promise, a prediction written in the temperature and humidity of the evening air. Imagine the night unfolding. The sun has set. The warmth that bathed the earth all day begins to radiate back into space. This is called radiative cooling, and it is the engine of dew formation. The ground, the grass, the leaves, all of these surfaces release their stored heat as infrared radiation, invisible light that streams upward into the atmosphere and beyond. On a clear night, with no clouds to reflect that warmth back down, the cooling is swift and profound. Surfaces can become much colder than the air just above them, and it is on these surfaces, these cool islands in the night, that dew is born. When a surface cools below the dew point of the surrounding air, the water vapor in contact with that surface begins to condense. Molecule by molecule, the invisible becomes visible. A single droplet of dew is a congregation of billions of water molecules, each one drawn from the air, each one slowing and binding to its neighbors in a delicate lattice of hydrogen bonds. These bonds are weak individually, but together they create the liquid state we recognize as water. The droplet clings to the surface, held by forces we'll explore more deeply as we go. And as the night continues, more droplets form, spreading across the landscape in a silent, glittering arrival. Dew forms most abundantly on certain kinds of surfaces. Grass is one of the finest collectors of dew the natural world has ever produced. Each blade is thin, with a high surface area relative to its volume. This means it cools quickly, often faster than the surrounding air. Grass also grows in dense clusters, creating a microenvironment near the ground where humidity is slightly higher and air movement is reduced. The result is a perfect stage for condensation. By dawn, a lawn can hold millions of tiny droplets, each one a lens, each one catching the early light. Leaves, too, are exceptional at gathering dew. Their broad, flat surfaces radiate heat efficiently, and many plants have evolved leaf structures that encourage water collection. Some leaves are waxy, allowing droplets to bead up rather than spread thin. Others have fine hairs or textures that provide nucleation sites, tiny imperfections where the first molecules of condensation can anchor themselves. In tropical forests, where humidity is high and nights are warm, dew can form even on vertical surfaces, trickling down bark and pooling in the folds of large leaves. In temperate regions, dew is most generous in late summer and early autumn, when warm days give way to cool, clear nights. Metal surfaces, stones, and glass also collect dew, though each behaves slightly differently. Metal cools rapidly because it conducts heat well, pulling warmth away from its surface and releasing it into the air. A car parked outside on a clear night will often be covered in dew by morning, its hood and roof transformed into mirrors of tiny water beads. Glass, being a poor conductor, cools more slowly, but still reaches the dew point on many nights. Windows facing the sky often weep with condensation, especially if the interior of a building is warmer and more humid than the outside air. Stone, depending on its type and texture, can either shed dew quickly or hold it in its pores, slowly releasing it as the sun rises. The size of a dew droplet is a marvel in itself. Most droplets range from a fraction of a millimeter to a few millimeters in diameter. They are small enough to cling to surfaces through surface tension, yet large enough to catch and scatter light. Surface tension is the force that makes water droplets spherical, the result of water molecules pulling on each other more strongly than they pull on the air around them. This creates a kind of skin on the droplet's surface, a molecular membrane that resists breaking. It's the same force that allows insects to walk on water, and it's what gives dew its jeweled appearance. The shape of a dew droplet depends on the surface it rests upon. On a waxy leaf or a well-polished car, where water does not adhere strongly, droplets form nearly perfect spheres, minimizing their contact with the surface. On rough or porous materials, droplets spread out more, forming flatter shapes. The angle at which a droplet meets a surface is called the contact angle, and it reveals the balance between the water's cohesion to itself and its adhesion to the surface. Hydrophobic surfaces, like lotus leaves, have high contact angles, and water beads up dramatically. Hydrophilic surfaces, like untreated wood, have low contact angles, and water spreads thin. Dew does not form uniformly across a landscape. Even within a single garden, some areas will be drenched while others remain dry. This variation is due to microclimates, tiny pockets of differing temperature and humidity created by the shape of the land, the presence of plants, and the movement of air. Low-lying areas, where cold air settles, often have the heaviest dew. Hilltops and slopes, where air drains away, may have little or none. Areas sheltered from the wind collect more dew because the air remains still, allowing humidity to build. Exposed areas, where breezes blow, lose moisture and warmth more quickly, and dew formation is reduced. The clarity of the sky plays a profound role. On a cloudy night, the clouds act as a blanket, trapping the heat radiating from the earth and reflecting it back down. The ground cools more slowly, and the dew point may not be reached. But on a clear night, with no clouds to interrupt the flow of infrared radiation, the cooling is unimpeded. The surface temperature can drop 10 or even 15 degrees below the air temperature, just a meter above. This is when dew is most abundant, when the night is open and the stars are sharp. Wind, even a gentle breeze, can prevent dew from forming. Moving air constantly replaces the layer of humid air near a surface with drier air from elsewhere. This makes it harder for the air immediately touching the surface to reach saturation. On perfectly still nights, the air near the ground becomes stratified, with the coolest, most humid layer resting directly on the dew-collecting surfaces. This is the condition dew loves best: stillness, clarity, and coolness. The temperature difference required for dew to form is often surprisingly small. Sometimes just a degree or two of cooling is enough to cross the dew point threshold. This is especially true in humid climates, where the air is already laden with moisture. In arid regions, the air must cool much more before condensation begins, and dew is correspondingly rare. But even in deserts, under the right conditions, dew can form. It may be sparse, appearing only on the coolest surfaces, but it is there, a testament to the persistence of water. Dew is most commonly associated with morning, but it can form at any time when the conditions are right. In some climates, dew begins to appear in the late evening, just an hour or two after sunset. In others, it doesn't form until the deepest part of the night, when the earth has shed as much heat as it can. The timing depends on how quickly the surface cools, which in turn depends on the material, the weather, and the season. The amount of dew that forms in a single night is modest, but not insignificant. On a particularly favorable night, a square meter of grass might collect a few tenths of a millimeter of water, equivalent to a very light drizzle. Over the course of a year, in a region with frequent dew, this can add up to several liters per square meter. For plants, especially in regions where rain is infrequent, this moisture can be vital. Some species have evolved to capture and channel dew toward their roots, using specialized leaf shapes and surface textures. There are plants in the Namib Desert, one of the driest places on Earth, that survive almost entirely on dew and fog. The air near the coast is often humid, thanks to the cold ocean currents, and at night, this moisture condenses on the plant's leaves. By morning, enough water has accumulated for the plant to absorb, sustaining it through the rainless months. This is one of the most elegant adaptations in the natural world, a partnership between atmosphere and organism, mediated by the simple physics of condensation. Animals, too, benefit from dew. In arid environments, insects and small mammals often drink from dew-covered plants at dawn. Some beetles in the Namib have evolved a remarkable behavior. They climb to the tops of dunes in the early morning and tilt their bodies into the fog-laden wind. Water condenses on their backs and trickles down grooves in their exoskeletons toward their mouths. This behavior, called fog basking, is a direct response to the availability of atmospheric moisture, and it has inspired engineers designing water collection systems for human use. Birds, especially small songbirds, often drink dew droplets from leaves and grass. In dry seasons, when streams and puddles have vanished, dew can be one of the few reliable sources of fresh water. Reptiles, too, lick dew from rocks of vegetation. The moisture is pure, free from the salts and minerals that accumulate in standing water, and it provides hydration without the need to travel to distant water sources. Dew has a purity that rain often lacks. Raindrops form high in the atmosphere, where they gather dust, pollen, and pollutants as they fall. Dew, by contrast, condenses directly from the air onto surfaces, bypassing much of this contamination. It is not perfectly pure. There are always trace amounts of dissolved gases and particles, but it is remarkably clean. In some cultures, Dew has been collected for drinking, for cooking, and even for medicinal purposes, valued for its freshness and clarity. The formation of dew is a phase transition, a change in the state of matter from gas to liquid. Phase transitions are among the most fundamental processes in physics, governed by the laws of thermodynamics. When water vapor condenses into liquid, it releases energy. This energy, called latent heat, is the same energy that was required to evaporate the water in the first place. The release of latent heat during condensation warms the surrounding air very slightly, a tiny pulse of warmth in the cooling night. This effect is subtle, but it plays a role in the energy balance of the lower atmosphere. The process of condensation begins at the molecular level. Water molecules in the vapor phase are in constant motion, colliding with each other and with surfaces. When a molecule strikes a surface that is below the dew point, it may lose enough energy to stick. If more molecules join it, a cluster forms. This cluster can grow into a droplet, or it can evaporate again if the conditions change. The earliest stages of dew formation are probabilistic, a dance of chance and energy. But once a droplet reaches a certain size, it becomes stable and continues to grow. Nucleation is the term for the initial formation of a droplet. Homogeneous nucleation, where droplets form spontaneously in pure air, is extremely rare. It requires very high levels of supersaturation, far beyond what occurs in normal dew formation. Instead, dew relies on heterogeneous nucleation, where droplets form on surfaces or on tiny particles in the air. Dust, pollen, bacteria, and even salt crystals from the ocean can serve as nucleation sites. These particles provide a surface for the first water molecules to cling to, lowering the energy barrier for condensation. The presence of nucleation sites is one reason why dew forms more readily on some surfaces than others. A perfectly smooth, clean surface might resist dew formation because there are few places for the initial molecules to anchor. A rough or dirty surface, by contrast, offers countless nucleation sites, and dew appears quickly and abundantly. This is why car windshields, which are often coated with a thin layer of dust and pollen, collect dew so readily. The temperature at which dew forms is not always the same as the air temperature. Because surfaces cool faster than the surrounding air, the surface temperature can be several degrees lower. Meteorologists use instruments called dew point hygrometers to measure the dew point of the air, but the actual temperature at which dew forms on a given surface depends on that surface's properties. This is why dew can appear on grass, even when the air temperature is well above the dew point measured at a weather station. The dew point itself is influenced by the amount of water vapor in the air, which is measured as humidity. Relative humidity is the ratio of the current amount of water vapor to the maximum amount the air can hold at that temperature. When relative humidity reaches 100%, the air is saturated, and any further cooling will cause condensation. Absolute humidity, by contrast, measures the actual mass of water vapor per unit volume of air, regardless of temperature. Both measures are useful, but for dew formation, the dew point is the most direct and meaningful value. Humidity varies throughout the day in a predictable rhythm. It is usually highest in the early morning, just before sunrise, when the air is coolest and has had all night to accumulate moisture from evaporation and transpiration. It is lowest in the afternoon, when the air is warmest and can hold the most vapor without condensing. This daily cycle is driven by temperature, but it is also influenced by wind, weather systems, and proximity to bodies of water. In coastal regions, the ocean is a vast reservoir of moisture. Evaporation from the sea surface pumps water vapor into the air continuously, keeping humidity high. On calm nights, this moisture-laden air settles over the land, and dew forms abundantly. Inland regions, especially those far from large lakes or rivers, tend to be drier, and dew is less frequent. But even in the heart of a continent, Dew can form after a rain, when the soil is wet and evaporation has enriched the air with moisture. Transpiration, the process by which plants release water vapor through their leaves, also contributes to humidity. A single large tree can transpire hundreds of liters of water in a day, much of which enters the local atmosphere. At night, when transpiration slows, this moisture remains in the air, available for condensation. Forests, with their dense canopies and high transpiration rates, create humid microclimates where dew is common and generous. The color of dew is usually clear, but can take on tints depending on what it condenses upon. Dew on green leaves may appear faintly green, reflecting the chlorophyll beneath. Dew on red petals may seem to blush. This is not because the water itself is colored, but because the droplets act as lenses, magnifying and transmitting the colors of the surfaces they rest on. In bright sunlight, dew droplets can sparkle with all the colors of the spectrum, tiny prisms splitting light into its constituent wavelengths. The optical properties of dew are a source of endless fascination. Each droplet is a sphere of water, and spheres are natural lenses. Light entering a droplet is refracted, bent by the change in density from air to water. Some of this light reflects off the back surface of the droplet and exits again, creating a bright spot. This is why dew-covered grass can shimmer and glow in the morning sun, each blade adorned with points of light. Photographers and poets have long been captivated by this effect. The way dew transforms the ordinary into the luminous. Dew can also create optical phenomena on a larger scale. In certain conditions, dew on a field can produce a glory, a circular rainbow-like pattern visible when the sun is behind the observer. This is rare, but it demonstrates the complex interactions between light and water droplets. More commonly, dew contributes to the general softness of morning light, scattering and diffusing the sun's rays, creating a gentle, even illumination. The lifespan of a dew droplet is brief. As the sun rises and the air warms, the droplet begins to evaporate. The molecules at its surface gain energy and break free, returning to the vapor phase. Small droplets evaporate quickly, often within minutes of sunrise. Larger droplets can persist for an hour or more, especially if they are shaded or if the air remains cool. But by mid-morning, nearly all the dew is gone, reclaimed by the atmosphere, ready to begin the cycle again. Evaporation is the reverse of condensation, and it, too, is a phase transition. It requires energy, which is drawn from the droplet itself and from the surface it rests on. This is why evaporating dew has a cooling effect, a subtle but real contribution to the microclimate of a garden or field. In agricultural settings, this cooling can delay the warming of the soil in the morning, affecting when plants begin their daily photosynthesis. The rate of evaporation depends on temperature, humidity, and wind. On a hot, dry, breezy morning, dew vanishes almost as soon as the sun touches it. On a cool, humid, still morning, it lingers, sometimes until noon. This variability is part of what makes dew so responsive to local conditions, a sensitive indicator of the atmosphere's state. Dew is not the only form of atmospheric moisture that condenses on surfaces. Frost is similar to dew, but it forms when the surface temperature drops below the freezing point of water. Instead of liquid droplets, frost consists of ice crystals, intricate and delicate, each one a unique expression of the hexagonal symmetry of frozen water. Frost and dew can coexist on the same landscape, with frost forming in the coldest spots and dew in the slightly warmer ones. Fog is another related phenomenon. Fog is essentially a cloud that forms at ground level, consisting of countless tiny water droplets suspended in the air. It forms when the air itself cools to the dew point, rather than just the surfaces. Fog and dew often occur together, especially in valleys and near bodies of water. When fog droplets settle on surfaces, They contribute to the dew already forming there, creating especially heavy moisture. The study of dew has a long history. Ancient philosophers observed dew and speculated about its origins. Aristotle believed dew was a form of rain that fell so gently it was invisible. It wasn't until the development of thermodynamics in the 19th century that the true nature of dew was understood. Scientists like John Dalton and others explored the relationship between temperature, humidity, and condensation, laying the groundwork for modern meteorology. Today, dew is studied not only for its own sake, but also for what it reveals about the atmosphere. Dew formation is an indicator of radiative cooling, humidity levels, and surface properties. It can be used to infer the dew point without direct measurement, and it provides clues about the energy balance of the land surface. In climate science, understanding dew and other forms of condensation is essential for modeling the water cycle and predicting weather. Dew also has practical applications. In agriculture, dew can provide supplemental moisture to crops, especially in regions with dry summers. Some farmers design their irrigation systems to take advantage of dew, watering in the evening to increase humidity and encourage condensation overnight. In water-scarce regions, engineers have developed dew collection systems inspired by nature, using large surfaces to condense atmospheric moisture and channel it into storage tanks. The cultural significance of dew is rich and varied. In literature and poetry, dew often symbolizes purity, renewal, and the quiet beauty of dawn. It appears in religious texts, in folklore, and in songs. The ephemeral nature of dew, its brief existence between night and day, has made it a metaphor for transience and the fleeting moments of life. Yet there is also something eternal about dew, the way it returns every clear night, a faithful presence in the rhythm of the natural world. In this first part of our journey, we've begun to understand what dew is and how it forms. We've seen how the cooling of surfaces, the humidity of the air, and the stillness of the night come together to create those tiny, glistening droplets. We've explored the physics of condensation, the role of nucleation sites, and the conditions that favor dew formation. We've touched on the ways plants and animals use dew, and the optical beauty it brings to the morning landscape. There is so much more to discover. The story of dew is also the story of the atmosphere, of energy and molecules, of the delicate balance between liquid and vapor. It is a story written in the language of thermodynamics, but it speaks to something deeper, something about the quiet generosity of the natural world, the way water moves endlessly between earth and sky, giving and receiving, never truly lost. As we continue, we'll delve deeper into the science, exploring the molecular forces that hold a droplet together, the role of temperature gradients, and the ways dew interacts with different materials. We'll look at the variations in dew formation across climates and seasons, and we'll consider the broader implications of this simple, beautiful process. For now, rest in the knowledge that dew is forming somewhere, even now, as you listen. On a blade of grass, on a petal, on a cool stone, water is gathering, molecule by molecule, silent and patient, waiting for the light. The geometry of dew droplets follows principles that have fascinated scientists for centuries, and the way these tiny spheres take shape on different surfaces reveals something profound about the balance between forces at the molecular scale. When water condenses on a leaf or a blade of grass, it doesn't spread out into a thin film unless the surface chemistry encourages it. Instead, surface tension pulls the water molecules together, minimizing the area exposed to air, and this creates the rounded bead we recognize as a droplet. The contact angle, the angle at which the droplet's edge meets the surface, tells us about the relationship between water and that particular material. On waxy leaves, the angle is steep, and droplets sit high and rounded, almost spherical. On more wettable surfaces, the angle is shallow, and the water spreads slightly, forming a flatter dome. This interplay between adhesion and cohesion is quiet, invisible to the casual observer, but it determines the shape, size, and behavior of every drop that forms in the early hours. The size of dew droplets is not random. It emerges from a balance between the rate of condensation, the temperature gradient, and the availability of nucleation sites on the surface. Most dew droplets range from a fraction of a millimeter to a few millimeters in diameter, small enough to cling without falling, large enough to catch light and shimmer. As condensation continues, droplets grow, and neighboring droplets may merge when they touch, forming larger beads in a process called coalescence. This merging is gentle, almost meditative to watch in time-lapse footage. Two droplets approach, touch, and suddenly become one, the surface tension pulling them together in an instant. The new droplet is rounder, more stable, and it may slide slightly on the surface, pulled by gravity or the slope of the leaf. Over the course of the night, the surface may host thousands of these tiny unions, each one a small rearrangement of water and energy. The maximum size a droplet can reach before it falls depends on the strength of its adhesion to the surface and the angle of that surface. On a horizontal leaf, droplets can grow quite large, sometimes several millimeters across, before gravity overcomes the adhesive force and they roll or drip away. On a vertical surface, droplets are smaller because gravity pulls them downward as they grow. The texture of the surface matters too. Rough surfaces with microscopic peaks and valleys can hold droplets more securely because the water settles into the tiny grooves and gains additional contact points. Smooth surfaces offer less grip, and droplets may slide or roll with only a slight disturbance. This is why dew on grass often seems more abundant and persistent than dew on polished metal or glass. The grass provides countless tiny anchors, while the smooth surface offers little resistance to movement. The color of dew droplets, or rather the way they interact with light, adds another layer of beauty to the phenomenon. Pure water is essentially colorless, but dew droplets act as tiny lenses and prisms, bending and reflecting light in ways that create visual effects. When sunlight strikes a droplet at the right angle, it can refract through the water, reflect off the back surface, and exit again, sometimes producing a small spectrum of colors. This is the same principle behind rainbows, though on a much smaller scale. The effect is subtle, often requiring close observation or the right lighting conditions to notice. In the soft light of dawn, dew-covered grass can appear to glow, each droplet catching and scattering the low-angle rays of the sun. The overall effect is one of quiet radiance, a field transformed into a constellation of tiny lights. The thermal properties of dew droplets influence their persistence through the morning. Water has a high specific heat capacity, meaning it takes a significant amount of energy to raise its temperature. This property allows dew droplets to remain cool even as the surrounding air begins to warm at the sunrise. The droplets absorb heat slowly, and as they do, they begin to evaporate, returning to the atmosphere as water vapor. The rate of evaporation depends on several factors: air temperature, humidity, wind speed, and the amount of sunlight striking the droplets. On a calm, humid morning, dew may linger for hours, slowly diminishing as the day progresses. On a dry, breezy morning, it may vanish within minutes of sunrise, the droplets evaporating so quickly that the ground seems to dry almost instantly. The process of evaporation is endothermic, meaning it requires energy, and this energy is drawn from the surrounding environment. As dew evaporates, it cools the surface it rests on, providing a brief, localized cooling effect. This is one reason why mornings with heavy dew can feel slightly cooler than mornings without it, even if the air temperature is the same. The evaporating water carries heat away, a small but measurable contribution to the microclimate of the surface. For plants, This cooling can be beneficial, especially in climates where daytime temperatures rise quickly. The dew provides a buffer, a few extra minutes or hours of cooler conditions before the full heat of the day arrives. Dew formation is not limited to natural surfaces. It occurs on cars, windows, rooftops, and any other object that cools below the dew point during the night. The dew that forms on a car windshield is chemically and physically identical to the dew on a leaf, though the surface properties differ. Glass is smooth and relatively hydrophilic, meaning water spreads more easily on it than on a waxy leaf. The result is often a thin, even layer of tiny droplets that can obscure visibility until they are wiped away or evaporate. On metal surfaces, dew can contribute to corrosion over time, as the water facilitates chemical reactions between the metal and oxygen in the air. This is why objects left outdoors in humid climates often show signs of rust or oxidation, a slow process driven in part by the nightly accumulation of dew. The measurement of dew is a subtle science. Meteorologists and researchers use instruments called drosometers to quantify the amount of dew that forms over a given period. A simple drosometer might consist of a flat plate of known area, placed outdoors overnight and weighed before and after dew formation to determine the mass of water collected. More sophisticated instruments use sensors to detect changes in surface moisture or temperature, providing continuous data on dew formation and evaporation. These measurements help scientists understand local and regional patterns of moisture availability, which in turn inform studies of agriculture, ecology, and climate. In some regions, dew contributes a measurable fraction of the total water input to ecosystems, and tracking this contribution requires careful, patient observation. The chemistry of dew is generally simple, but it can carry traces of the atmosphere through which it forms. As water vapor condenses, it can dissolve small amounts of gases present in the air, including carbon dioxide, oxygen, and nitrogen. In polluted areas, dew may also absorb sulfur dioxide, nitrogen oxides, or particulate matter, becoming slightly acidic or contaminated. This is why dew in urban or industrial areas can sometimes have a different pH or chemical composition than dew in rural or remote regions. Plants and animals that rely on dew for hydration may be affected by these differences, though the concentrations are usually low enough that the impact is minimal. Still, dew serves as a subtle indicator of air quality, a liquid record of the atmosphere's composition at the moment of condensation. The diurnal cycle of dew formation and evaporation is a rhythm that countless organisms have adapted to over evolutionary time. Some plants have evolved leaf structures that maximize dew collection, channeling water toward the base of the plant where roots can absorb it. Others have waxy coatings that cause dew to bead up and roll off, preventing prolonged wetness that could encourage fungal growth. Animals, too, have developed behaviors around dew. Certain beetles in the Namib Desert, for example, have specialized surfaces on their backs that attract dew from fog, allowing them to drink in an environment where liquid water is otherwise scarce. These adaptations are testaments to the importance of dew as a resource, a reliable source of moisture in the quiet hours before dawn. The relationship between dew and frost is one of temperature and phase. Both involve water vapor condensing on surfaces, but frost forms when the surface temperature is at or below the freezing point of water. Instead of liquid droplets, frost consists of ice crystals, delicate structures that grow directly from vapor to solid in a process called deposition. The transition between dew and frost is not always sharp. On nights when temperatures hover around freezing, dew may form first, and then freeze into ice as temperatures continue to drop. The result is a mix of liquid and solid, a transitional state that reflects the narrow boundary between the two phases of water. Understanding this transition is important for agriculture, as frost can damage crops while dew generally does not. The optical phenomenon known as the dew bow is a rare and beautiful occurrence. similar to a rainbow, but formed by dew droplets rather than raindrops. When the sun is low on the horizon and the observer is positioned correctly, sunlight can refract and reflect through dew droplets on grass or other low vegetation, creating a faint arc of colors. Dew bows are typically smaller and fainter than rainbows, and they require very specific conditions to be visible. The droplets must be numerous and uniformly distributed. The sun must be at the right angle, and the observer must be looking in the right direction. When all these factors align, the result is a fleeting, ethereal display, a reminder of the intricate ways light and water interact. The sound of dew is almost non-existent, yet there is a certain quietness associated with it, a stillness that seems to accompany its presence. In the early morning, before the wind picks up and the world stirs, the silence is profound. The dew contributes to this quietness in subtle ways. Wet surfaces absorb sound differently than dry ones, dampening echoes and softening footsteps. The air itself, heavy with moisture, carries sound differently, often making distant noises seem muffled or muted. This acoustic quality of dewy mornings is part of their charm, a sensory experience that goes beyond the visual. The distribution of dew across a landscape is uneven, shaped by microtopography and local conditions. Low-lying areas, where cold air settles, often receive more dew than elevated areas. Surfaces that face the open sky cool more efficiently and collect more dew than surfaces shaded by trees or buildings. Even within a single field, dew can vary significantly from one spot to another, creating a patchwork of wet and dry zones. This variability is important for plants and animals, as it creates microhabitats with different moisture levels. A beetle seeking water might move from a dry hilltop to a damp valley, guided by the gradient of dew availability. The persistence of dew through the morning depends not only on temperature and humidity, but also on the albedo of the surface, its reflectivity. Dark surfaces absorb more sunlight and warm more quickly, causing dew to evaporate faster. Light-colored surfaces reflect more sunlight and stay cooler longer, allowing dew to linger. This is why dew on pale stones or light-colored leaves may persist longer than dew on dark soil or asphalt. The interplay between color, temperature, and moisture is a quiet dance, one that unfolds differently on every surface and every morning. The role of dew in seed germination is subtle but significant. For some plant species, especially those in arid or semi-arid regions, dew provides the moisture necessary for seeds to begin the germination process. Seeds lying on the soil surface may absorb water from dew, swelling and activating the biochemical processes that lead to sprouting. This can occur even in the absence of rain, making dew a critical factor in the life cycle of certain plants. The timing of dew formation, its frequency, and its duration all influence whether a seed will successfully germinate, and this in turn shapes the composition of plant communities across the landscape. The cultural significance of dew extends beyond its practical and ecological roles. In many traditions, dew is associated with purity, renewal, and the quiet magic of the early morning. Poets and writers have long used dew as a symbol of freshness and fleeting beauty, a natural phenomenon that appears and vanishes with the turning of the day. In folklore, dew collected at certain times, such as on May Day or Midsummer's Eve, was believed to have special properties, capable of bestowing beauty, health, or good fortune. These beliefs, while not scientifically grounded, reflect a deep human connection to the rhythms of nature and the small wonders that mark the passage of time. The study of dew has practical applications in fields ranging from agriculture to architecture. Farmers use knowledge of dew patterns to time irrigation, apply pesticides, and predict frost risk. Architects and engineers consider dew formation when designing buildings, especially in humid climates where condensation on windows and walls can lead to mold or structural damage. Understanding the conditions that promote or prevent dew formation allows for better management of resources and environments, a quiet application of science to everyday challenges. The relationship between dew and atmospheric pressure is indirect but real. High-pressure systems, which often bring clear skies and calm winds, create ideal conditions for dew formation. Low-pressure systems, associated with clouds and precipitation, inhibit dew by keeping temperatures more uniform and reducing radiative cooling. Meteorologists use this relationship as one of many indicators when forecasting weather, recognizing that the presence or absence of dew can signal broader atmospheric patterns. A morning without dew, in a place where it is usually common, might suggest an approaching weather change, a shift in the balance of pressure and moisture. The physics of dew droplets includes fascinating details about surface energy and stability. A droplet on a surface is in a state of equilibrium, balancing the forces of gravity, surface tension, and adhesion. If disturbed, the droplet may oscillate briefly, its surface rippling before settling back into a stable shape. This oscillation is governed by the same principles that describe waves on a pond, a connection between the very small and the larger scales of fluid dynamics. Watching a droplet respond to a vibration or a breath of wind is to witness fundamental physics in action, a demonstration of how matter organizes itself according to universal laws. The evaporation of dew is not uniform across a droplet surface. The edges of a droplet, where the water is thinnest, evaporate more quickly than the center, where the water is deeper. This creates a gradient of evaporation rates within a single droplet, a microscopic version of the way a puddle dries from its edges inward. As the edges evaporate, the droplet shrinks and changes shape, becoming smaller and more rounded until it finally disappears. This process is slow and continuous, a gradual return of water to the atmosphere that mirrors the gradual condensation that formed the droplet in the first place. The interaction between dew and soil is a topic of interest in hydrology and agriculture. When dew forms on soil surfaces, it can penetrate the top layer, providing moisture to the uppermost roots of plants. In sandy soils, which drain quickly, this surface moisture may be especially important as it lingers longer than rainwater that percolates downward. In clay soils, which hold water more tightly, dew adds to the overall moisture content, contributing to the slow, steady availability of water for plants. The amount of dew that infiltrates the soil depends on the soil's texture, structure, and initial moisture level, as well as the rate of dew formation and the duration of its presence. The phenomenon of dew on spider webs is one of nature's most delicate visual spectacles. Spider silk is extremely fine, often just a few micrometers in diameter, and it provides an ideal substrate for dew condensation. The silk cools rapidly at night, and its surface properties allow water droplets to form at regular intervals along the strands. The result is a web adorned with dozens or hundreds of tiny beads, each one catching the light and making the entire structure visible. Without dew, many spider webs will be nearly invisible, their silk too fine to see against most backgrounds. Dew transforms them into temporary works of art, revealing the hidden architecture of the spider's creation. The spacing of dew droplets on spider silk is not random. It follows a principle known as the Rayleigh plateau instability, which describes how a liquid film on a thin fiber will break up into droplets to minimize surface energy. The droplets form at regular intervals, determined by the diameter of the silk and the properties of the water. This same principle governs the behavior of liquids on wires, threads, and other thin structures, and it is a beautiful example of how mathematics and physics manifest in the natural world. The spider, of course, has no knowledge of these principles, yet its web becomes a demonstration of them every dewy morning. The acoustic properties of a dew-covered landscape are subtly altered by the presence of moisture. Sound waves travel differently through humid air than through dry air, and wet surfaces absorb and reflect sound in distinct ways. In a dew-covered meadow, footsteps are quieter and distant sounds seem softer. This is partly due to the moisture in the air and partly due to the way wet grass and soil interact with sound waves. The overall effect is a sense of muffled calm, a sonic quality that complements the visual softness of the dewy scene. The formation of dew on human-made structures can have unintended consequences. On solar panels, for example, dew can reduce efficiency by scattering incoming sunlight before it reaches the photovoltaic cells. However, dew can also help clean the panels, washing away dust and debris as it evaporates. On bridges and other infrastructure, dew can contribute to corrosion, especially if the water contains dissolved pollutants. Engineers must account for these effects when designing structures for humid environments, selecting materials and coatings that resist moisture-related damage. The global distribution of dew is shaped by climate zones and seasonal patterns. Dew is most common in temperate and subtropical regions, where nights are cool and humidity is moderate to high. In tropical regions, high nighttime temperatures often prevent surfaces from cooling below the dew point, so dew is less frequent. In arid regions, low humidity limits the amount of water vapor available for condensation, though dew can still form under the right conditions. Polar regions experience dew during their brief summers, when temperatures rise above freezing and liquid water can exist on surfaces. Understanding these patterns helps scientists model water cycles and predict how climate change might alter the distribution and frequency of dew. The role of dew in the water balance of ecosystems is often underestimated. In some environments, dew can contribute as much as 10 to 20% of the annual moisture input, a significant fraction that supports plant growth and animal survival. This is especially true in coastal regions, where humid air from the ocean provides abundant water vapor, and in mountainous areas, where cool nights and clear skies promote radiative cooling. Researchers measure dew as part of broader studies of ecohydrology, seeking to understand how water moves through landscapes and sustains life. The interaction between dew and pollutants is a growing area of research. As dew forms, it can capture aerosols, dust, and other particles from the air, effectively scrubbing the atmosphere on a small scale. When the dew evaporates, some of these particles are deposited on the surface, while others may be re-released into the air. This process can affect air quality, soil chemistry, and plant health. In agricultural settings, dew can carry pesticides or fertilizers from plant surfaces to the soil, influencing the distribution and impact of these chemicals. Understanding these interactions is important for managing environmental health and agricultural practices. The formation of dew on leaves can influence photosynthesis, the process by which plants convert sunlight into energy. A thin layer of dew can act as a lens, focusing sunlight onto the leaf surface and potentially increasing the light intensity experienced by the photosynthetic cells. However, if the dew layer is too thick or persists too long, it can block sunlight and reduce photosynthesis. The balance between these effects depends on the size and distribution of the droplets, the angle of the sunlight, and the duration of the dew's presence. Plants have evolved to tolerate and even benefit from these daily fluctuations. Their physiology adapted to the rhythms of dew formation and evaporation. The scent of a dewy morning is subtle but distinct, a freshness that seems to arise from the earth itself. This scent is partly due to the release of volatile organic compounds from plants and soil, which are more readily detected in the cool, moist air. Dew can also dissolve and carry these compounds, spreading them across the landscape as droplets form and evaporate. The result is a complex bouquet of earthy, green, and floral notes, a sensory signature of the early morning that many people find calming and pleasant. The study of dew has historical roots that stretch back centuries. Ancient Greek and Roman naturalists observed and wrote about dew, speculating on its origins and properties. In the Middle Ages, alchemists believed dew had special qualities, and they collected it for use in their experiments. The scientific understanding of dew began to develop in the 17th and 18th centuries, as researchers like William Wells conducted systematic observations and experiments. Wells' work on the cooling of surfaces and the role of radiative heat loss laid the foundation for modern dew science, and his insights remain relevant today. The relationship between dew and human comfort is subtle but real. On a humid morning, the presence of dew can make the air feel cooler and fresher, even if the temperature is the same as on a dry morning. This is partly a psychological effect, as the visual and sensory cues of dew signal coolness and moisture. It is also partly physiological, as the evaporation of dew from surfaces and the higher humidity in the air affect the body's ability to cool itself through perspiration. The overall experience is one of gentle coolness, a quality that many people find soothing and restorative. The formation of dew on grass is so common that it is often taken for granted, yet it represents a remarkable convergence of physical processes. Each blade of grass, with its narrow shape and large surface area relative to its volume, is an efficient radiator of heat. As the grass cools, it reaches the dew point before the surrounding air, and water vapor begins to condense on its surface. The result is a field of countless tiny droplets, each one a miniature world of physics and chemistry. Walking through dew-covered grass, feeling the cool moisture on your skin, is to engage directly with this process, to become part of the cycle of water and energy that defines the morning. The temporal patterns of dew formation are remarkably consistent, yet they vary with the seasons and the weather. In spring and autumn, when nights are cool and days are warm, dew is frequent and abundant. In summer, especially in humid regions, dew may form even on relatively warm nights, as the high moisture content of the air allows condensation at higher temperatures. In winter, dew is less common, replaced by frost when temperatures drop below freezing. These seasonal rhythms are part of the larger cycles of nature, the ebb and flow of moisture and temperature that shape the living world. The role of dew in the lives of amphibians is particularly important. Frogs, toads, and salamanders rely on moist environments to keep their skin hydrated, as they breathe partly through their skin and lose water rapidly in dry conditions. Dew provides a source of moisture that allows these animals to venture into areas that might otherwise be too dry. A frog sitting on a dew-covered leaf is not just resting. It is absorbing water through its skin, replenishing its hydration, and maintaining its physiological balance. This interaction between animal and environment is a quiet testament to the interconnectedness of life. The measurement of dew point, the temperature at which air becomes saturated and dew begins to form, is a fundamental tool in meteorology. Dew point is a direct indicator of the amount of moisture in the air, and it is often a better measure of humidity than relative humidity, which depends on both moisture content and temperature. A high dew point indicates humid air, while a low dew point indicates dry air. Meteorologists use dew point to forecast weather, predict fog, and assess the risk of frost. For anyone interested in understanding the atmosphere, dew point is a key concept, a bridge between the abstract idea of water vapor and the tangible reality of dew on the ground. The formation of dew on feathers is a phenomenon observed in birds that roost outdoors overnight. Feathers are excellent insulators, but their outer surfaces can cool below the dew point, especially on clear, calm nights. Water droplets form on the feather tips, and in the morning, a bird may appear lightly dusted with moisture. The bird's preening behavior, running its beak through its feathers, helps to distribute the water and maintain the feather's waterproofing. This daily interaction with dew is part of the bird's routine, a small but essential aspect of its life in the wild. The relationship between dew and moonlight is poetic but also physical. On nights with a full moon, the landscape is bathed in soft, reflected sunlight, and dew droplets can catch and scatter this light, creating a faint shimmer across fields and meadows. The effect is subtle, visible only to the patient observer, but it adds a layer of beauty to the night. Moonlight does not significantly affect the formation of dew, as the radiative cooling that drives condensation depends on the emission of infrared radiation from the surface, not on the presence or absence of visible light. Yet the coincidence of moonlight and dew creates a scene of quiet enchantment, a reminder of the many ways light and water interact. The evaporation of dew is a process of returning, a completion of the cycle that began with condensation. As the sun rises and the air warms, the dew droplets begin to shrink, their molecules gaining energy and escaping back into the atmosphere as vapor. The rate of evaporation increases with temperature and wind speed, and it decreases with humidity. On a still, humid morning, dew may linger for hours, slowly diminishing as the day progresses. On a breezy, dry morning, it may vanish within minutes, leaving no trace behind. This variability is part of the charm of dew, a phenomenon that is both predictable and ever-changing, shaped by the unique conditions of each morning. The molecular dance that creates each droplet unfolds with precision that feels almost musical. Water molecules in the air move constantly, vibrating and tumbling through space, each one carrying kinetic energy that determines its speed and trajectory. When a molecule encounters a cool surface, it doesn't simply stick immediately. Instead, it approaches, contacts, and may bounce away several times before finally releasing enough energy to remain attached. This process happens countless times each second across every square centimeter of surface, building the thin film that will eventually gather into visible droplets. The surface itself plays an active role in this capture, its molecular structure reaching out with weak forces that tug at passing water molecules. Some surfaces possess what scientists call nucleation sites, tiny imperfections or chemical variations that make it easier for water molecules to begin clustering together. A microscopic scratch, a speck of dust, or a slight variation in surface chemistry can become the birthplace of a droplet that will eventually grow large enough to catch the morning light. The temperature gradient between air and surface creates what you might think of as a one-way door for water molecules. Warm air holds more energetic water molecules that move faster and resist condensing. As this air contacts the cooler surface, the molecules near the boundary slow down, losing kinetic energy to the solid material beneath them. This cooling happens in a thin layer, sometimes only millimeters thick, creating a zone where the rules change and water vapor transforms into liquid. The thickness of this boundary layer depends on wind speed and temperature difference. On perfectly still nights, it can extend several centimeters above the surface, an invisible realm where transformation occurs gradually. When gentle breezes stir the air, this layer compresses, becoming thinner but also more efficient at bringing fresh, humid air into contact with the cooling surface. The balance between stillness and movement determines how quickly dew can form and how much moisture the night will deliver. Beyond the immediate surface, the entire column of air above participates in dew formation through a process called radiative cooling. As night falls and the sun's warming influence fades, the ground begins releasing the heat it accumulated during the day. This heat radiates upward as infrared energy, invisible to our eyes, but carrying thermal energy into space. On clear nights, this radiation escapes freely, allowing the ground to cool rapidly. The air immediately above the ground cools through contact, creating the temperature drop necessary for condensation. Cloud cover acts like a blanket, reflecting some of this infrared radiation back toward the surface and slowing the cooling process. This explains why cloudy nights produce less dew than clear ones. The clouds themselves don't block dew formation directly. Instead, they interrupt the radiative cooling that makes it possible. A single layer of high, thin clouds can reduce dew formation by half, while thick low clouds can prevent it almost entirely. The chemistry of the surface matters as much as its temperature. Hydrophilic surfaces, those that attract water molecules, encourage dew formation by providing favorable sites for condensation to begin. Many plant leaves possess microscopic structures and chemical coatings that make them particularly good at capturing dew. These surfaces don't just passively collect moisture, they actively draw it from the air through molecular attraction. Waxy coatings on some leaves create a different effect, causing water to bead up into nearly perfect spheres that roll and gather rather than spreading into films. This hydrophobic property serves important functions for the plant, helping shed excess water that might harbor fungi or block sunlight from reaching the leaf surface. The interplay between hydrophilic and hydrophobic zones on a single leaf can create intricate patterns of dew distribution, with some areas collecting dense moisture while adjacent regions remain relatively dry. The size distribution of dew droplets follows patterns that emerge from the physics of growth and coalescence. Initial condensation creates countless tiny droplets, each barely large enough to scatter light. These microdroplets, sometimes only a few micrometers across, form first on the most favorable nucleation sites. As more water vapor condenses, some droplets grow larger while others remain small, creating a population with a wide range of sizes. The larger droplets grow faster because they present more surface area for additional molecules to attach to, a positive feedback loop that accelerates their expansion. Meanwhile, the smallest droplets may actually shrink, losing molecules to the air or to nearby larger droplets through a process driven by surface tension differences. This leads to a characteristic size distribution where most droplets fall within a certain range, with fewer very small and very large droplets at the extremes. Gravity begins to influence droplets once they reach a certain size, typically around 1 to 2 millimeters in diameter. At this threshold, the weight of the water overcomes the surface tension holding it in place, and the droplet may slide, drip, or roll depending on the surface angle and texture. On horizontal surfaces, droplets can grow quite large before gravity becomes important, sometimes reaching 3 or 4 millimeters across. On vertical or steeply angled surfaces, droplets remain smaller because they slide away before accumulating much mass. This creates different dew patterns on different parts of the same object. The top of a car may be covered in large, nearly spherical droplets, while the windshield displays smaller droplets that have slid partway down before evaporating or merging with others. These patterns reflect the constant negotiation between condensation, which adds water, and gravity, which removes it. The rate of dew formation varies through the night, following the cooling curve of the surface. Maximum formation typically occurs in the hours just before dawn, when surface temperatures reach their lowest point and the temperature difference between air and surface peaks. Early evening may see little dew even if temperatures have dropped, because the surface is still releasing stored heat and hasn't cooled below the dew point. As the night progresses and radiative cooling continues, the surface temperature gradually falls, crossing the dew point threshold and initiating condensation. The rate accelerates as the temperature gap widens, reaching a maximum in the pre-dawn hours. This timing means that much of the dew you see at sunrise formed in just the last few hours of night, a rapid accumulation that can deposit surprising amounts of water in a short time. Wind patterns interact with dew formation in complex ways that depend on speed, direction, and turbulence. Gentle air movement can actually enhance dew formation by bringing fresh, humid air into contact with cool surfaces, replacing air that has already released some of its moisture. This convective mixing prevents the formation of a dry layer immediately above the surface, maintaining a supply of water vapor for continued condensation. However, stronger winds disrupt this process by preventing the surface from cooling sufficiently. The constant mixing brings warmer air down to the surface, replacing the cool boundary layer before it can drop below the dew point. Wind speeds above about 2 or 3 meters per second typically prevent significant dew formation, while speeds below 1 meter per second create ideal conditions. The threshold varies depending on other factors like humidity and temperature, but the general principle holds across different environments. The vertical distribution of dew on vegetation reveals how different heights experience different microclimates. Grass blades close to the ground often collect the most dew because they cool most rapidly, being in direct contact with the cooling soil. Mid-height vegetation, such as the stems and lower leaves of shrubs, may receive less dew because they're insulated somewhat from the ground's radiative cooling. Upper leaves and branches exposed to the open sky can accumulate significant dew through their own radiative cooling, even if they're not in contact with the ground. This creates a vertical pattern where dew is abundant at ground level, less common at intermediate heights, and present again in the canopy. The pattern shifts depending on plant density, with dense vegetation creating more uniform conditions and sparse vegetation showing more variation. Dew formation on artificial structures follows principles similar to natural surfaces, but with some unique characteristics. Metal surfaces, being good conductors of heat, cool rapidly and can become quite efficient dew collectors. However, their smooth surfaces often lack nucleation sites, which can delay the onset of condensation. Once dew begins forming, though, it can accumulate quickly, sometimes creating enough moisture to drip like light rain. Glass surfaces behave similarly, cooling rapidly on clear nights and collecting dense dew layers. The transparency of glass creates interesting optical effects, with dew droplets acting as tiny lenses that distort and magnify whatever lies behind them. Plastic surfaces vary widely in their dew-collecting properties, depending on their chemical composition and surface texture. Some plastics are hydrophobic and shed dew readily, while others attract and hold moisture effectively. The thermal mass of an object influences how much dew it can collect. Objects with low thermal mass, like thin leaves or fabric, cool quickly and reach the dew point early in the evening, potentially collecting more total moisture over the course of the night. Objects with high thermal mass, like thick wooden posts or stone walls, cool slowly and may not reach the dew point until late in the night, limiting their dew accumulation. However, once these massive objects cool below the dew point, they can maintain that temperature longer into the morning, continuing to collect dew even after sunrise when thin objects are already warming and losing their moisture. This difference creates temporal patterns where some surfaces are wet in early evening while others remain dry, and some surfaces stay wet well into the morning while others dry quickly. The color and reflectivity of surfaces affect their cooling rates, and thus their dew formation potential. Dark surfaces absorb more solar radiation during the day, storing more heat, but they also radiate more efficiently at night, potentially cooling faster once the sun sets. Light-colored surfaces absorb less heat during the day and radiate less at night, leading to more moderate temperature swings. The net effect on dew formation depends on the balance between these factors. In general, surfaces that can radiate heat efficiently tend to collect more dew, regardless of color. However, in environments where daytime heating is intense, dark surfaces may remain too warm for too long, reducing their total dew accumulation compared to lighter surfaces that start the cooling process from a lower initial temperature. The geometry of surfaces creates microclimates that affect dew distribution. Horizontal surfaces facing the sky radiate heat most efficiently and typically cool most rapidly, making them prime locations for dew formation. Vertical surfaces radiate heat in all directions, including toward the ground and adjacent objects, which can slow their cooling. Surfaces facing downward, like the underside of leaves or overhangs, radiate toward the ground, which is also cooling and radiating back, creating a more balanced energy exchange that results in slower cooling and less dew. This geometric effect explains why the tops of objects are usually wetter than their sides or bottoms. The angle of a surface relative to the sky determines how efficiently it can radiate heat into space, with angles near horizontal being most effective. Dew formation creates temporary ecosystems that exist only during the wet hours. Microscopic organisms, including bacteria, algae, and fungi, become active when dew appears, using the moisture to metabolize, reproduce, and move. Some bacteria can actually enhance dew formation on the surfaces where they live by producing proteins that act as nucleation sites, making it easier for water vapor to condense. These biological nucleation sites can be more effective than purely physical features, allowing condensation to begin at temperatures slightly above the normal dew point. The organisms benefit from the extended period of moisture availability, while the surface benefits from having dew form earlier and persist longer. This mutual relationship represents a subtle form of environmental engineering carried out at the microscopic scale. The chemical composition of dew differs from rain in subtle but important ways. Rainwater forms high in the atmosphere and falls through layers of air, potentially collecting pollutants along the way, but also benefiting from some purification as it passes through clouds. Dew forms directly on surfaces from water vapor that has been in contact with the ground-level environment, often making it more concentrated in whatever chemicals are present in the local air. In urban areas, dew can contain higher concentrations of nitrogen compounds, sulfur compounds, and particulates than rain. In coastal areas, dew may be slightly saline from sea spray particles that serve as nucleation sites. In agricultural regions, dew can contain traces of fertilizers, pesticides, and soil particles. These chemical signatures make dew a useful indicator of local air quality, capturing a sample of the immediate atmospheric environment. Plants have evolved numerous adaptations to maximize dew collection and use. Some desert plants possess specialized leaf structures with channels and grooves that direct dew toward the stem and roots, effectively harvesting atmospheric moisture. Others have dense coatings of fine hairs that increase surface area and provide abundant nucleation sites, allowing them to collect more dew than their smooth-leaf neighbors. Certain succulents can absorb water directly through their leaves, taking up dew before it evaporates in the morning sun. These adaptations are particularly important in arid environments where dew may represent a significant portion of the plant's water budget. In some desert ecosystems, dew can provide more moisture than rain during certain seasons, making these adaptations critical for survival. The optical properties of individual dew droplets create the visual beauty we associate with dewy mornings. Each droplet acts as a tiny lens, refracting and reflecting light according to the same principles that govern rainbows and other optical phenomena. When sunlight enters a droplet, it slows down and bends, separating into its component colors. Some of this light reflects off the back surface of the droplet and exits, having been bent twice and reflected once. This is the same path that creates rainbows, though individual droplets are too small to produce visible color separation to the naked eye. Instead, they create points of bright white light, each droplet a tiny star. When millions of droplets cover a surface, they create a field of light that can be breathtaking, especially when viewed with the sun at the right angle behind you. The lifetime of a dew droplet depends on multiple factors that begin changing the moment the sun rises. Solar radiation warms the droplet and its supporting surface, increasing the kinetic energy of water molecules and making it easier for them to escape back into the air. The air temperature rises, increasing its capacity to hold water vapor and creating a gradient that draws moisture away from the droplet. Wind may pick up as the day begins, bringing drier air into contact with wet surfaces and accelerating evaporation. Under typical conditions, dew begins evaporating within minutes of sunrise, though droplets in shaded areas or on surfaces with high thermal mass may persist for hours. The largest droplets evaporate more slowly than small ones because they have less surface area relative to their volume, giving them a longer lifetime. A large droplet might take 30 minutes to evaporate completely, while a tiny droplet might vanish in seconds. The sound of dew is subtle but real. As droplets grow large enough to fall from leaves or other surfaces, they make tiny impacts, creating soft taps and plinks that are usually inaudible to human ears, but can be detected with sensitive microphones. In dense vegetation, after a particularly heavy dew, the accumulated sound of thousands of falling droplets creates a gentle patter similar to very light rain. This acoustic signature is different from rain, being quieter and more irregular, but contributes to the soundscape of early morning. Some animals may use these sounds as cues, recognizing the acoustic pattern of dew as distinct from rain and adjusting their behavior accordingly. The sound also indicates moisture availability, potentially guiding animals toward areas where drinking water has accumulated. Dew formation on spider webs creates some of nature's most photographed scenes. Spider silk is an excellent dew collector because of its fine diameter and hydrophilic properties. The silk's protein structure attracts water molecules, and its thinness allows it to cool rapidly below the dew point. As dew condenses along the length of each strand, surface tension causes it to gather into evenly spaced beads, creating a pattern like a string of pearls. This beading occurs because the silk isn't perfectly uniform. Tiny variations in thickness or chemistry create preferred sites where water accumulates. The droplets then grow and pull together, leaving dry sections between them. The resulting pattern is both beautiful and functional, as the beaded structure maintains the web's integrity better than a continuous water film would. The weight of the dew can make the web visible when it would otherwise be nearly invisible, revealing the intricate architecture that the spider constructed. The relationship between dew and frost represents a phase transition boundary that depends on surface temperature. When the surface temperature is above freezing but below the dew point, water vapor condenses as liquid dew. When the surface temperature is below freezing, water vapor can deposit directly as ice crystals, forming frost without passing through the liquid phase. This direct gas-to-solid transition is called deposition, and it creates crystal structures quite different from frozen dew. True frost has a feathery, crystalline appearance, while frozen dew looks more like ice glaze. The transition temperature isn't exactly 0 degrees Celsius because of the way water behaves at small scales and in the presence of dissolved substances. Dew can remain liquid at temperatures slightly below freezing, especially if it contains dissolved salts or other compounds that lower its freezing point. This supercool dew is unstable and can freeze rapidly if disturbed. Atmospheric pressure affects dew formation through its influence on the dew point temperature. At higher elevations, where atmospheric pressure is lower, the dew point for a given amount of water vapor is slightly different than at sea level. This effect is usually small compared to other factors like temperature and humidity, but becomes noticeable in mountainous regions. Lower pressure also affects the rate of evaporation and condensation, changing the dynamics of how quickly dew can form and how long it persists. In high-altitude environments, the combination of lower pressure, intense solar radiation, and often lower humidity creates conditions where dew formation is less common and less abundant than at lower elevations. However, in high-altitude cloud forests, frequent fog provides moisture that condenses on surfaces in a process similar to dew formation, sometimes called fog drip or horizontal precipitation. The cultural significance of dew spans human history and geography. Ancient peoples observed dew as a mysterious gift from the night sky, appearing without rain and providing moisture when none seemed available. Many cultures developed spiritual or mythological explanations for dew, seeing it as tears of gods, breath of the earth, or manifestation of cosmic forces. These beliefs weren't merely superstition. They reflected careful observation of a real phenomenon that had practical importance. Dew could mean the difference between crop success and failure in marginal agricultural lands. It could provide drinking water for travelers and herders. Its presence or absence could signal changing weather patterns. This practical importance elevated due to symbolic significance, making it a subject of poetry, proverbs, and religious texts across many traditions. Traditional agricultural practices in many regions explicitly account for dew. Farmers learned to plant certain crops in locations or configurations that maximize dew collection, improving plant health without irrigation. Some traditional farming systems used mulches or ground covers that enhanced dew formation, creating microclimates with higher moisture availability. In viticulture, dew patterns influence grape health and wine quality, with some vineyard sites prized partly for their dew characteristics. Too much dew can promote fungal diseases, while too little can stress vines during dry periods. Understanding the dew patterns of a site is part of the traditional knowledge that distinguished skilled farmers from novices, a body of practical meteorology passed down through generations. The measurement of dew has evolved from simple observation to sophisticated instrumentation. Early methods involved placing absorbent materials like cloth or wood blocks outside overnight and weighing them in the morning to determine how much moisture they had collected. These methods were crude but effective, providing quantitative data about dew deposition rates. Modern dew measurement uses electronic sensors that can detect the presence of moisture on a surface and measure its accumulation over time. These sensors work through various principles, including changes in electrical resistance or capacitance when water is present. Some research stations use artificial surfaces designed to mimic natural materials while providing standardized measurement conditions. The data collected helps scientists understand dew patterns, validate climate models, and assess the role of dew in local water budgets. Dew formation contributes to weathering and erosion processes over long time scales. The repeated wetting and drying of rock surfaces creates stresses that can crack and fracture the material. Water that condenses in tiny cracks can dissolve minerals, gradually widening the cracks through chemical weathering. In cold climates, dew that freezes and cracks expands, exerting force that can split rocks apart. These processes are slow, operating over decades or centuries, but they're relentless. Ancient structures show the effects of countless dew cycles, with stone surfaces becoming pitted and roughened. The pattern of weathering often reflects the pattern of dew formation, with surfaces that collect more dew showing more degradation. This makes dew a sculptor of landscapes, working alongside rain, wind, and temperature changes to shape the physical world. The energy balance of dew formation involves subtle exchanges that affect local climate. When water vapor condenses in a liquid, it releases latent heat, the energy that was required to evaporate the water in the first place. This heat release warms the surface slightly, creating a negative feedback that slows further cooling. The amount of heat released depends on how much dew forms. A heavy dew can release enough energy to raise the surface temperature by a degree or two. This warming is usually small compared to other energy flows, but it can be enough to prevent frost formation on nights when temperatures are near freezing. Surfaces with heavy dew may remain slightly warmer than dry surfaces nearby, creating temperature variations across a landscape. These microclimatic differences can affect where frost forms, which plants survive cold nights, and how ecosystems arrange themselves in space. Dew plays a role in air quality through a process called wet deposition. Particles suspended in the air, including dust, pollen, and pollutants, can serve as nucleation sites for dew formation. As droplets form around these particles, they effectively remove them from the air, temporarily improving air quality. When the dew evaporates, the particles may be left on the surface rather than returning to the air, providing a net cleaning effect. This process is less efficient than rain at removing particles, but it operates more frequently and can have cumulative effects. In urban environments, dew can remove significant amounts of particulate matter from the air over time, depositing it on buildings, vehicles, and vegetation. The surfaces become dirty, but the air becomes cleaner, at least until wind or human activity resuspends the particles. The relationship between dew and disease in plants is complex and important for agriculture. Many fungal pathogens require liquid water on leaf surfaces to germinate and infect plants. Dew provides this water, creating conditions favorable for disease development. Plant pathologists study dew duration and frequency as key factors in disease forecasting models. A sequence of nights with heavy dew can trigger disease outbreaks, while dry periods can interrupt disease cycles. Farmers sometimes use dew forecasts to time fungicide applications, treating crops just before conditions become favorable for infection. Some agricultural practices aim to reduce dew formation in crop canopies, using plant spacing, pruning, or site selection to promote air circulation and faster drying. These practices represent applied understanding of dew physics, using knowledge of condensation processes to manage biological threats. The chemistry of surfaces changes when dew is present, affecting everything from corrosion rates to biological activity. Metals exposed to dew can corrode more rapidly than in dry conditions, as the water provides a medium for electrochemical reactions. The rate of corrosion depends on what's dissolved in the dew. Pollutants like sulfur dioxide or nitrogen oxides can make dew acidic, accelerating metal degradation. This is why outdoor metal structures in humid climates often show more corrosion than similar structures in dry climates, even if the dry climate has higher temperatures. Protective coatings and treatments are designed with dew in mind, creating barriers that prevent moisture from contacting the underlying metal. Understanding dew chemistry is essential for predicting the lifespan of infrastructure and designing materials that can withstand repeated wetting cycles. Dew formation on vehicles creates familiar patterns that reflect the physics of cooling and condensation. Car windshields often collect more dew than other parts because glass cools efficiently through radiative heat loss and lacks internal heat sources. Metal body panels may collect less dew if the engine or interior retains heat that keeps them above the dew point. The pattern of dew on a car can reveal details about its thermal properties and recent use. A car that was driven recently may have a warm engine that keeps the hood dry while the roof and trunk are wet. A car parked in the open will have more dew than one under a tree, which receives less sky exposure and therefore radiates heat less efficiently. These patterns are mundane but instructive, demonstrating condensation principles in everyday contexts. The seasonal variation in dew formation follows patterns linked to temperature, humidity, and day length. In temperate climates, late summer and early fall often bring the heaviest dews, as warm days provide abundant evaporation and clear nights allow efficient cooling. Spring can also be a season of significant dew as temperatures moderate and humidity increases. Winter typically sees less dew because cold air holds less moisture, though dew can still form on nights when temperatures are above freezing and humidity is high. Summer may have less dew in some regions despite high humidity because nights are short and temperatures don't drop as much before sunrise. These seasonal patterns affect ecosystems, agriculture, and human activities, creating rhythms that living things have adapted to over evolutionary time. The interaction between dew and soil moisture creates feedback loops that can affect local water availability. Dew that forms on soil surfaces can infiltrate into the ground, adding to soil moisture reserves. In arid environments, this dew infiltration can be a significant water source for shallow-rooted plants. The presence of soil moisture, in turn, affects humidity levels near the ground, potentially increasing dew formation on subsequent nights. Dry soil provides less moisture to the air, potentially reducing dew formation. These feedbacks are usually weak compared to other factors like weather patterns, but they can become important in marginal environments where every bit of moisture matters. Understanding these interactions helps explain how some desert ecosystems maintain themselves despite minimal rainfall. Dew formation in urban environments differs from natural settings in several ways. Buildings, pavement, and other artificial surfaces create a heat island effect, keeping urban areas warmer than surrounding rural areas. This warmth can reduce or eliminate dew formation in city centers while nearby countryside experiences heavy dew. However, urban areas also have sources of moisture, including irrigation, air conditioning, and human activities, which can increase local humidity. The net effect varies by city, season, and weather conditions. Some urban surfaces, like glass and metal, are excellent dew collectors when they do cool below the dew point. Others, like asphalt and concrete, may collect less dew because they retain heat or have surface properties that discourage condensation. The mosaic of surfaces in cities creates complex dew patterns that reflect the built environment's thermal and chemical diversity. The chemistry of dew holds within it a quiet complexity that unfolds molecule by molecule in the darkness before dawn. When water vapor transforms into liquid droplets on a blade of grass, it is not merely changing state, but engaging in an intricate dance of hydrogen bonds, each molecule reaching out to its neighbors with invisible arms of attraction. The water molecule itself is a simple trinity, two hydrogen atoms bonded to one oxygen atom in a bent configuration that creates a permanent dipole, a slight positive charge on one side and a slight negative charge on the other. This asymmetry gives water its remarkable properties, its ability to cling to itself and to other surfaces, its capacity to dissolve so many substances, its unusual density behavior that allows ice to float. In the formation of dew, these molecular characteristics become visible poetry written across the landscape. The hydrogen bonds that form between water molecules are weaker than the covalent bonds that hold each molecule together, yet they are strong enough to create the cohesion that allows liquid water to exist at Earth's temperatures. Each water molecule in a dew droplet can form up to 4 hydrogen bonds with its neighbors, creating a dynamic network that constantly breaks and reforms trillions of times per second. This molecular restlessness gives liquid water its fluidity while maintaining enough structure to hold a droplet's shape against gravity. The energy required to break these bonds is considerable, which is why water has such a high heat capacity and why evaporation requires so much energy. When dew forms, the reverse process releases that energy into the environment as latent heat, a gentle warming that slightly moderates the cooling of surfaces through the night. The surface of a dew droplet is a place of particular molecular interest, where water molecules experience forces different from those in the bulk liquid. Molecules of the surface have neighbors only on one side and below, creating an imbalance of forces that produces surface tension, that invisible skin that allows droplets to bead and insects to walk on water. The surface tension of water is remarkably high compared to most liquids, a direct consequence of those strong hydrogen bonds pulling the surface molecules inward. This tension is what gives dew droplets their characteristic rounded shapes, minimizing surface area for a given volume. The curved surface of a droplet also affects the vapor pressure slightly, a phenomenon described by the Kelvin equation, where smaller droplets require higher relative humidity to remain stable than larger ones. This is why dew tends to form first as larger droplets rather than as a mist of tiny ones. Within the droplet, dissolved gases from the atmosphere create a dilute solution that is never quite pure water. Carbon dioxide dissolves readily, forming carbonic acid that makes dew slightly acidic with a pH typically around 5.6. Oxygen and nitrogen dissolve in smaller amounts. Their solubility, depending on temperature and pressure according to Henry's law. These dissolved gases can affect the chemistry of surfaces where dew forms, slowly weathering minerals and stone, or contributing to the corrosion of metals. In polluted air, other gases may dissolve as well, sulfur dioxide and nitrogen oxides that can make dew significantly more acidic, sometimes dropping the pH below 4 in industrial areas. This acidic dew can damage sensitive plant tissues and accelerate the degradation of building materials, a slow chemical weathering that occurs night after night. The process of nucleation, the initial formation of liquid from vapor, requires overcoming an energy barrier that depends on the curvature of the forming droplet. Homogeneous nucleation, the spontaneous formation of droplets in pure air without any surface, requires such extreme supersaturation that it almost never occurs in nature. Instead, dew formation relies on heterogeneous nucleation, where water vapor condenses onto existing surfaces that lower the energy barrier. The microscopic texture of these surfaces matters greatly, with tiny pits and scratches providing ideal nucleation sites where water molecules can gather and begin forming stable clusters. A perfectly smooth surface would be less effective at promoting dew formation than one with microscopic roughness, even though both might feel smooth to the touch. The contact angle that a water droplet makes with a surface reveals much about the molecular interactions between water and that material. On hydrophilic surfaces, where water molecules are attracted to the surface molecules, the contact angle is small and droplets spread out into thin films. On hydrophobic surfaces, where water molecules are more attracted to each other than to the surface, the contact angle is large and droplets bead up into nearly spherical forms. This angle is determined by the balance of three interfacial tensions: between water and air, between water and the solid, and between the solid and air. Young's equation describes this balance mathematically, though in practice the contact angle can vary depending on whether the droplet is advancing across the surface or receding from it, a phenomenon called contact angle hysteresis that reflects the complexity of real surfaces. The isotopic composition of dew provides a fingerprint of its origin and formation conditions. Water molecules containing different isotopes of hydrogen and oxygen have slightly different masses, and this affects how readily they evaporate and condense. The heavier isotopes, deuterium and oxygen, 18, are slightly less likely to evaporate and slightly more likely to condense than their lighter counterparts. This fractionation means that dew is typically enriched in heavy isotopes compared to the water vapor from which it formed. By measuring these isotope ratios with mass spectrometry, scientists can trace the sources of atmospheric moisture and understand the history of water as it cycles through the environment. Dew formed from local evaporation has a different isotopic signature than dew formed from moisture that traveled long distances, allowing researchers to map invisible pathways of water through the atmosphere. The thermal conductivity of water plays a subtle role in dew formation, determining how quickly heat can be transferred through the growing droplet. Water conducts heat better than air, but not as well as metals, with a thermal conductivity of about 0.6 watts per meter per Kelvin. As a droplet grows, the latent heat released by condensation must be conducted away through the droplet to the cooled surface beneath, or else the droplet would warm and slow its own growth. For very small droplets, this heat transfer is rapid and not limiting, but for larger droplets or thick dew accumulations, the rate of heat conduction can become a factor that moderates the rate of condensation. This is one reason why dew formation slows as the night progresses and droplets grow larger. The electrical properties of water and dew droplets create subtle but measurable effects in the atmosphere. Pure water is a poor conductor of electricity, but the dissolved ions always present in natural do make it slightly conductive. Dew droplets can acquire small electrical charges through various mechanisms, including the preferential adsorption of ions onto their surfaces and the capture of charged aerosol particles. These charges are typically small, but they can influence the behavior of droplets, causing them to attract or repel each other slightly and affecting their interaction with surfaces. In the presence of atmospheric electric fields, which exist naturally even in fair weather, charged droplets can experience forces that subtly influence their shape and movement. The refractive index of water, approximately 1.33 for visible light, is responsible for the optical phenomena that make dew so visually enchanting. When light enters a water droplet from air, it slows down and bends according to Snell's law, the angle of refraction determined by the ratio of refractive indices. This bending allows droplets to act as tiny lenses, focusing light and creating bright spots and patterns. The refractive index varies slightly with wavelength, a property called dispersion, which is why droplets can sometimes separate white light into its component colors. The same physics that creates rainbows operates in dew droplets, though the small size and different viewing geometry usually make these effects more subtle. The evaporation of dew as morning progresses is governed by the same principles as its formation, but in reverse. As surfaces warm and air temperature rises, the vapor pressure of the liquid water in the droplets increases, while the dew point of the surrounding air may remain relatively constant. When the surface temperature exceeds the dew point, the droplets begin to evaporate, returning water molecules to the vapor phase. This evaporation requires energy, which is drawn from the surroundings as latent heat, providing a cooling effect that moderates the warming of surfaces in early morning. The rate of evaporation depends on temperature, humidity, and wind speed, with higher temperatures and lower humidity accelerating the process, while higher humidity slows it. The Clausius-Clapeyron equation describes how the saturation vapor pressure of water changes with temperature, a relationship fundamental to understanding both dew formation and evaporation. This equation shows that vapor pressure increases exponentially with temperature, which means that small temperature changes can have large effects on the balance between condensation and evaporation. At 10 degrees Celsius, the saturation vapor pressure of water is about 12.3 millibars, while at 20 degrees, it is about 23.4 millibars, nearly double. This exponential relationship explains why dew forms so readily when surfaces cool just a few degrees below the air temperature, and why it evaporates so quickly when the sun returns and surfaces warm. The heat capacity of water, the amount of energy required to raise its temperature, is unusually high compared to most substances. It takes about 4.2 joules of energy to raise 1 gram of water by 1 degree Celsius, a value that reflects the energy needed to increase the kinetic energy of the molecules, while also partially disrupting the hydrogen bond network. This high heat capacity means that dew droplets act as tiny thermal buffers, resisting rapid temperature changes and moderating the microclimate around them. When dew evaporates, it absorbs a large amount of energy from its surroundings, about 2,400 joules per gram, providing significant evaporative cooling that can keep plant surfaces cooler than they would otherwise be as the morning sun rises. The viscosity of water, its resistance to flow, affects how dew droplets behave on sloped surfaces and how they coalesce when they meet. Water has a relatively low viscosity compared to oils or honey, about 1 millipascal second at room temperature, which allows droplets to flow and merge readily. This low viscosity is why dew droplets can quickly coalesce when they touch, their surfaces joining and the combined mass rearranging itself into a new spherical shape within milliseconds. The viscosity decreases with increasing temperature, which means that dew flows more easily in warmer conditions. though by the time temperatures rise enough to significantly affect viscosity, evaporation is usually already underway. The process of adsorption, distinct from absorption, describes how molecules can stick to surfaces in a layer, just one or a few molecules thick. Before visible dew droplets form, water molecules from the air adsorb onto surfaces, creating an invisible film that can be several molecular layers deep. This adsorbed water is held to the surface by van der Waals forces and hydrogen bonding with surface molecules, and it represents the earliest stage of dew formation. On hydrophilic surfaces, this adsorbed layer can be quite thick and stable, while on hydrophobic surfaces it is thinner and less stable. The transition from this adsorbed layer to visible droplets is gradual, with small clusters of water molecules growing and merging until they become large enough to see. The concept of water activity, related to but distinct from humidity, describes the availability of water for chemical and biological processes. Pure water has a water activity of 1, while solutions and materials with bound water have lower values. The water in dew droplets has a water activity close to 1, making it readily available for microorganisms and for dissolving substances. This high water activity is why dew can support microbial growth and why it is effective at dissolving salts and other soluble materials from surfaces. In contrast, the thin adsorbed layers that precede droplet formation have lower water activity because the water molecules are more tightly bound to the surface. The phenomenon of supercooling, where liquid water remains unfrozen below its normal freezing point, can occur in dew droplets under certain conditions. Pure water can supercool to temperatures as low as -40 degrees Celsius if it is free of nucleation sites that would trigger ice formation. Dew droplets, however, usually contain dissolved substances and are in contact with surfaces that can serve as ice nuclei, so they typically freeze close to 0 degrees Celsius. When supercooled dew droplets do freeze, they release latent heat of fusion, about 334 joules per gram, which briefly warms the immediate surroundings. The resulting ice crystals, called frost when formed directly from dew, have a different appearance and structure than frost formed directly from vapor. The Kelvin effect, also called the Gibbs-Thomson effect, describes how the vapor pressure over a curved surface differs from that over a flat surface. For water droplets, the vapor pressure is slightly higher over the curved surface than it would be over a flat water surface at the same temperature. This effect becomes more pronounced as droplets become smaller, which means that very small droplets are less stable and require higher relative humidity to avoid evaporating. This is why dew tends to form as droplets of a certain minimum size rather than as an ultra-fine mist, and why smaller droplets tend to evaporate first when conditions become less favorable. The Kelvin effect is described mathematically by an equation involving surface tension, molecular volume, and droplet radius. The presence of surfactants, molecules that concentrate at interfaces and reduce surface tension, can alter dew formation and droplet behavior. Natural surfactants in the atmosphere, including certain organic compounds from plants and microorganisms, can be incorporated into dew droplets and modify their properties. Surfactants lower the surface tension of water, which reduces the energy required to create new surface area and can promote the spreading of droplets on surfaces. In polluted environments, anthropogenic surfactants from industrial processes and combustion can also be present in dew, sometimes creating thin films or unusual droplet shapes. The study of surfactants in atmospheric water is an active area of research with implications for cloud formation and air quality. The dielectric constant of water, a measure of how well it can store electrical energy in an electric field, is unusually high at about 80 at room temperature. This high dielectric constant is why water is such an excellent solvent for ionic compounds, as it effectively shields dissolved ions from each other and prevents them from recombining. In dew droplets, this property allows for the dissolution and dissociation of salts and other ionic substances, creating solutions that can conduct electricity and participate in electrochemical reactions. The high dielectric constant also affects how electromagnetic radiation interacts with water, which is relevant to remote sensing techniques that detect moisture using microwave or infrared sensors. The process of Ostwald ripening describes how larger droplets can grow at the expense of smaller ones, even without direct contact. Because of the Kelvin effect, smaller droplets have higher vapor pressure than larger ones, which means that in a field of mixed-sized droplets, water molecules will tend to evaporate from small droplets and condense onto large ones. This process slowly shifts the size distribution toward fewer, larger droplets over time. In dew formation, Ostwald ripening is usually a minor effect compared to direct coalescence and continued condensation from the air, but can play a role in the later stages of the night when temperature and humidity have stabilized and droplet growth has slowed. The acoustic properties of dew, though subtle, can be detected with sensitive instruments. The formation of droplets, their coalescence, and their eventual fall from leaves all create tiny vibrations and sounds, mostly at frequencies too high or too quiet for human hearing. Researchers have used sensitive microphones and accelerometers to detect these sounds, finding that different plants and surfaces produce characteristic acoustic signatures as dew forms. This acoustic approach to monitoring dew is still experimental, but it offers a non-invasive way to study the process in real time without disturbing the droplets themselves. The sounds of dew formation blend into the broader acoustic landscape of the night, a hidden layer of the natural soundscape. The role of atmospheric aerosols in dew formation extends beyond their function as condensation nuclei. Aerosol particles can also affect the radiative properties of the atmosphere, influencing how much infrared radiation escapes to space and thus affecting the rate of surface cooling. Certain aerosols, particularly those that are hygroscopic, can take up water from the air even before the dew point is reached, growing into wet particles that can serve as precursors to dew droplets. These wet aerosols can also affect visibility, creating haze that scatters light and reduces clarity. In urban areas, the high concentration of aerosols can lead to more numerous, but smaller dew droplets compared to rural areas with cleaner air. The concept of nucleation rate describes how frequently new droplets form on a surface per unit area per unit time. This rate depends on temperature, supersaturation, and the properties of the surface. At low supersaturation, just below the dew point, the nucleation rate is very low and few droplets form. As the surface cools further below the dew point, the supersaturation increases and the nucleation rate rises exponentially. This is why dew formation often seems to accelerate as the night progresses and surfaces continue to cool, with more and more droplets appearing in a positive feedback process. The mathematical description of nucleation rate comes from classical nucleation theory, which treats the formation of a new droplet as a thermally activated process that must overcome an energy barrier. The interaction between dew and pollutants creates a complex chemistry that can affect both air quality and ecosystem health. Dew droplets can scavenge pollutants from the air, including particulate matter, gases, and volatile organic compounds, effectively removing them from the atmosphere and depositing them on surfaces. This process, called wet deposition, is an important pathway for the removal of air pollutants, though it can also concentrate these substances on plant leaves and other surfaces where they may cause harm. Some pollutants, once dissolved in dew, can undergo chemical reactions that transform them into other compounds, sometimes more harmful, sometimes less so. The study of dew chemistry is thus an important part of understanding air pollution and its effects. The formation of dew on spider webs creates structures of particular beauty and scientific interest. Spider silk is hydrophobic, which causes dew droplets to bead up into nearly perfect spheres rather than spreading out. The regular spacing of the silk strands creates a periodic array of droplets that can produce optical effects similar to a diffraction grating, separating light into its component colors. The weight of the dew droplets can also cause the web to sag and deform, changing its geometry in ways that affect how it captures prey. Some spiders rebuild their webs each morning, in part because the accumulation of dew and debris reduces their effectiveness, while others simply remove the dew by shaking the web or allowing it to evaporate. The temporal dynamics of dew formation follow a pattern that can be predicted and modeled. Typically, dew begins to form an hour or two after sunset, as surfaces cool below the dew point. The rate of dew accumulation is often highest in the middle of the night when the temperature difference between the surface and the air is greatest. Toward dawn, as the air itself cools and its capacity to hold moisture decreases, the rate of dew formation may slow even though surfaces continue to cool. The total amount of dew accumulated through the night represents a balance between condensation, which adds water, and evaporation, which can remove it if conditions fluctuate. Mathematical models of dew formation incorporate these temporal dynamics, using equations that describe heat and mass transfer to predict when and how much dew will form. The concept of dew yield, the amount of water that can be collected from dew, has practical applications in water harvesting. In arid regions where rain is scarce but humidity is relatively high at night, specially designed surfaces can collect significant amounts of dew. These surfaces are typically made of materials with high thermal emissivity to maximize radiative cooling, combined with hydrophilic properties to promote droplet formation and drainage. Dew yield varies greatly with location and season, typically ranging from 0.1 to 0.5 millimeters per night, equivalent to 100 to 500 liters per hectare. While this is much less than rain, in some ecosystems it represents a significant fraction of total water input and can be the difference between survival and desiccation for plants and animals during dry seasons. The microphysics of droplet growth involves the continuous addition of water molecules to the droplet surface. Each molecule that joins the droplet must give up its kinetic energy of motion as it transitions from gas to liquid, and this energy is released as heat for a single molecule. This energy is tiny, but for the billions of molecules that condense to form even a small droplet, the cumulative heat release is measurable. This latent heat must be conducted away from the droplet, primarily through the surface on which it sits, or the droplet will warm and its growth will slow. The rate at which molecules join the droplet depends on the vapor pressure in the surrounding air, the temperature of the droplet surface, and the rate at which heat can be removed. The study of dew using remote sensing techniques has advanced significantly in recent decades. Satellites equipped with thermal infrared sensors can detect the cooling of surfaces at night, and by comparing surface temperatures with air temperatures from weather stations, scientists can estimate where and when dew is likely forming. Microwave radiometers can detect the presence of liquid water on vegetation, allowing for the mapping of dew extent over large areas. These remote sensing approaches complement ground-based measurements and allow for the study of dew patterns at regional and continental scales. Such large-scale studies have revealed that dew formation is more widespread and significant than previously thought, particularly in semi-arid regions where it contributes meaningfully to the water budget. The interaction between dew and plant pathogens is a subject of considerable agricultural importance. Many fungal and bacterial plant diseases require free water on leaf surfaces to germinate and infect, and dew provides this water for extended periods. The duration of leaf wetness, the number of hours that leaves remain covered with dew or rain, is a key factor in disease forecasting models. Farmers and plant pathologists monitor leaf wetness using sensors that detect the presence of water through changes in electrical resistance or capacitance. By understanding the patterns of dew formation and persistence, they can predict disease outbreaks in time fungicide applications more effectively, reducing both crop losses and pesticide use. The phenomenon of dew drip, where dew droplets grow large enough to fall from leaves and other surfaces, represents a transfer of water from the canopy to the ground. In forests and other vegetated areas, dew drip can be a significant pathway for water movement, effectively redistributing atmospheric moisture to the soil. The size at which a droplet will fall depends on the strength of its adhesion to the surface, which is determined by surface tension and contact angle, and the force of gravity pulling it downward. For a droplet hanging from the underside of a leaf, the critical size is typically a few millimeters in diameter. When the droplet falls, it carries with it any dissolved substances it has accumulated, including nutrients and pollutants, which are then deposited in the soil or on lower vegetation. The cultural and historical significance of dew extends into the realm of alchemy and early chemistry. Dew was considered by alchemists to be a pure and potent substance, collected in the early morning for use in various preparations and experiments. They believed dew possessed special properties because it came from the sky and formed under the influence of the moon and stars. While these mystical beliefs have no scientific basis, the practice of collecting dew led to early observations about its properties and formation. Some of these observations, such as the recognition that dew forms more readily on clear nights and that it is essentially pure water, were accurate and contributed to the development of scientific understanding of atmospheric processes. The relationship between dew and atmospheric stability involves the vertical structure of the atmosphere near the ground. On clear, calm nights when dew forms most readily, the lower atmosphere typically develops a temperature inversion, where temperature increases with height rather than decreasing as it normally does. This inversion forms because the ground cools by radiation while the air above is insulated from this cooling. The inversion creates a stable stratification that suppresses vertical mixing and allows the near-surface air to become very humid as moisture evaporates from the soil and vegetation. This humid air then provides the moisture for dew formation, creating a feedback loop where dew formation and atmospheric stability reinforce each other. The microscopic examination of dew droplets reveals a world of complexity invisible to the naked eye. Under a microscope, the surface of a dew droplet appears smooth and featureless, a perfect liquid interface. But at higher magnifications, the molecular structure becomes relevant, and we can imagine the dynamic dance of water molecules at the surface, constantly evaporating and recondensing, moving in and out of the liquid phase. Dissolved particles and microorganisms within the droplet can be seen drifting and moving, propelled by Brownian motion and internal currents. The contact line where the droplet meets the surface shows the complex interaction between solid, liquid, and gas phases, with the exact position of this line fluctuating at the molecular scale. The energetics of dew formation can be quantified by considering all the energy flows involved. The primary energy loss is through long-wave radiation from the surface to the sky, typically on the order of 50 to 100 watts per square meter on a clear night. This energy loss is partially offset by downward radiation from the atmosphere, conduction of heat from the soil below, and the latent heat released by dew condensation. The net result is a cooling of the surface, but the rate of cooling is slower than it would be without dew formation. The latent heat released by dew can be significant, sometimes amounting to 10 or 20 watts per square meter, which is a substantial fraction of the total energy budget. This heating effect is one reason why surfaces with heavy dew formation cool more slowly than dry surfaces. The spatial patterns of dew formation across a landscape reflect the heterogeneity of surface properties and microclimates. In a meadow, some areas may be covered with heavy dew while others remain dry, depending on factors like vegetation type, soil moisture, and topography. Low-lying areas where cold air accumulates tend to have heavier dew, while hilltops exposed to wind may have little or none. The orientation of slopes affects how much sky they see and thus how much they cool by radiation, with surfaces facing the open sky cooling more than those sheltered by trees or buildings. These spatial patterns can be mapped and studied, revealing the complex interplay of factors that control dew formation and creating a mosaic of wet and dry microsites across the landscape. The chemistry of dew on different materials creates varied outcomes. On limestone and other carbonate rocks, the slightly acidic nature of dew can slowly dissolve the stone, carrying away calcium and carbonate ions in solution. Over centuries, this process can significantly weather stone surfaces, smoothing inscriptions and eroding architectural details. On iron and steel, dew promotes corrosion by providing the water necessary for oxidation reactions, leading to rust formation. On glass, dew is relatively inert, but dissolved minerals in the water can leave deposits when the dew evaporates, creating spots and streaks. On organic materials like wood and fabric, dew can promote the growth of mold and mildew by providing the moisture these organisms need. Each material interacts with dew in its own way, determined by the chemistry of its surface. The biological activity within dew droplets themselves can be surprisingly rich. Bacteria and other microorganisms present in the air or on the surface can become suspended in the droplet, where they find a temporary aquatic environment. Some bacteria are active in these droplets, metabolizing dissolved organic matter and reproducing. Fungi can germinate spores in the moisture, extending hyphae across the wet surface. Algae and cyanobacteria on rocks and bark can photosynthesize during the brief period when they are hydrated by dew. This biological activity transforms dew from a simple physical phenomenon into a dynamic microecosystem, a tiny aquatic world that exists for just a few hours before evaporating in the morning sun. The measurement of dew point temperature, the temperature at which air becomes saturated and dew begins to form, is a fundamental task in meteorology. Dew point can be measured directly using a chilled mirror hygrometer, which cools a mirror until dew condenses on it, and then measures the temperature at which this occurs. It can also be calculated from measurements of temperature and relative humidity using empirical equations. The dew point temperature is a more direct measure of atmospheric moisture content than relative humidity because it doesn't change with temperature. A high dew point indicates a large amount of moisture in the air, while a low dew point indicates dry air. Dew point temperatures are used in weather forecasting, aviation, and agriculture to predict fog, frost, and dew formation. The relationship between dew and soil moisture involves a subtle exchange that can be important in dry climates. When dew forms on the soil surface, it can infiltrate into the top layer of soil, increasing moisture content in the uppermost millimeters. This moisture can then be taken up by plant roots or evaporate back into the atmosphere as the day warms. In some ecosystems, particularly in arid regions with high nocturnal humidity, this dew infiltration represents a significant water input to the soil. The process is most effective on bare soil or sparse vegetation, where dew can form directly on the ground. On heavily vegetated surfaces, most dew forms on leaves and may evaporate without reaching the soil, though dew drip can transfer some water downward. The gentle rhythm of dew formation continues through every morning, a pattern as old as the atmosphere itself, repeating with quiet constancy across the surface of the world. Each droplet that forms represents a convergence of conditions, a moment when temperature, humidity, and surface meet in perfect balance. The process never tires, never falters, continuing through seasons and centuries with the same fundamental principles guiding each tiny bead of water into existence. In the deeper hours before dawn, when the earth has released most of its stored warmth into the open sky, the conditions for dew reach their most favorable state. The temperature gradient between surface and air steepens, creating an environment where water vapor finds every opportunity to transition into liquid form. Grass blades become collection points, each one a vertical surface intersecting the humid air, each one cooling slightly faster than the surrounding atmosphere, inviting condensation along its length. The molecular dance at the surface of a forming dew droplet involves thousands of water molecules arriving and departing each second, but with a net accumulation that gradually builds the visible drop. This dynamic equilibrium means that even a stationary droplet is never truly still at the molecular level. Water molecules evaporate from its surface while others condense onto it, creating a constant exchange that maintains the droplet size under stable conditions or allows it to grow when condensation exceeds evaporation. The shape of each droplet reflects the balance between surface tension pulling it into a sphere and gravity flattening it against the surface beneath. On a perfectly non-wetting surface, a droplet would form an almost perfect sphere, touching the surface at only a single point. On a more wettable surface, the droplet spreads, creating a flattened dome with a larger contact area. The contact angle, the angle where the droplet surface meets the underlying material, reveals the relationship between these forces, a geometric signature of the interaction between water and surface. Spider webs become galleries of dew in the early morning, each silk strand adorned with droplets spaced at regular intervals. The spacing emerges from the interplay between the strand's surface properties and the mechanical instability that causes small droplets to coalesce into larger, more widely separated ones. A freshly formed web may initially collect uniformly along its length, but surface tension quickly reorganizes this distribution into the characteristic beaded pattern, each droplet representing a local minimum of surface energy. The cooling that enables dew formation occurs most efficiently under specific atmospheric conditions, but the process adapts to a wide range of circumstances. Even when conditions are not ideal, some dew may form on the most favorable surfaces, those that cool most rapidly, or have surface properties that encourage condensation. This selective formation creates patterns across the landscape, with some areas heavily laden with dew, while nearby, surfaces remain dry, a mosaic determined by subtle variations in material, exposure, and microclimate. The thermal properties of dew have practical implications for the surfaces that bear it. The latent heat released during condensation warms the surface slightly, a small but measurable effect that can influence the temperature of delicate plant tissues. This warming is most significant during the period of most rapid dew formation, typically in the hours just after sunset when radiative cooling is most intense. As the night progresses and dew formation slows, this warming effect diminishes, and the surface temperature once again approaches equilibrium with the radiative cooling rate. Dew formation on agricultural crops represents a complex interaction between benefit and risk. The moisture can provide hydration to leaf surfaces, support the germination of fungal spores, and create conditions favorable for certain diseases. Farmers and agricultural scientists study dew patterns to understand disease risk, timing irrigation to avoid adding moisture when natural dew is already abundant, and selecting crop varieties with leaf architectures that either encourage rapid drying or, in arid regions, maximize dew collection. The optical properties of dew droplets extend beyond simple reflection and refraction to include more subtle effects. When light passes through a droplet at certain angles, it can undergo multiple internal reflections, creating interference patterns and colored fringes. These effects are usually too subtle to notice in individual droplets, but can contribute to the overall appearance of a dew-covered surface, adding a slight iridescence or color shift that changes with viewing angle. The study of dew has contributed to our understanding of atmospheric water cycles, particularly in regions where dew represents a significant fraction of total water input. In some coastal deserts, dew can provide more moisture than rainfall over the course of a year, making it a critical component of the local water budget. Researchers measure dew formation rates, analyze its chemical composition, and model its contribution to ecosystem water balance, building a more complete picture of how water moves through these environments. The sound of dew is almost imperceptible, a silence that contrasts with the audible patter of rain. Yet in the quietest moments, when dew droplets grow large enough to fall from leaves or coalesce into streams that trickle down stems, they create the faintest whisper of movement. This near silence is part of dew's character, a phenomenon that transforms the landscape without announcement, working in the quiet hours when few are present to witness it. The cultural significance of dew appears in literature, poetry, and spiritual traditions across many societies. Dew represents freshness, renewal, and the gifts of the night. It appears in metaphors for youth, purity, and transience. The ephemeral nature of dew, its appearance at dawn and disappearance by mid-morning, makes it a natural symbol for fleeting beauty and the passage of time. Writers and poets have drawn on this imagery for centuries, finding in dew a reflection of human experience. The formation of dew on human-made structures requires consideration in architecture and engineering. Buildings must manage the moisture that condenses on their surfaces, ensuring that it drains away without causing damage or creating slippery conditions. Metal roofs, glass facades, and painted surfaces all develop dew under the right conditions, and designers account for this in their plans, incorporating drainage channels, surface treatments, and materials that either shed water quickly or absorb it safely. The relationship between dew and frost is one of temperature threshold. Both form through similar processes, with water vapor condensing onto cooled surfaces. But frost occurs when the surface temperature drops below the freezing point of water. The transition between dew and frost is not always sharp. Sometimes dew forms first, and then freezes as temperatures continue to fall, creating ice crystals with a different structure than frost that forms directly from vapor. This frozen dew has a more compact, glassy appearance compared to the delicate crystalline structure of true frost. The study of dew on other planets and moons expands our understanding of condensation processes beyond Earth. Mars, with its thin atmosphere and extreme temperature variations, experiences frost formation in certain regions and seasons. The physics of condensation applies universally, but the specific conditions, the composition of the atmosphere, the nature of the surface, and the substances that condense vary from world to world. Studying these variations helps us understand both the unique characteristics of each planetary environment and the fundamental principles that govern phase transitions. The efficiency of dew formation depends on the availability of water vapor in the air, which in turn depends on temperature, pressure, and the presence of moisture sources. In coastal areas, the ocean provides an abundant source of water vapor, and dew forms readily on clear nights. Inland, especially in arid regions, the air may be too dry for significant dew formation even when other conditions are favorable. The amount of dew that forms reflects the local humidity, a direct measure of the atmosphere's moisture content. The interaction between dew and plant diseases has been studied extensively in agriculture. Many fungal pathogens require free water on leaf surfaces to germinate and infect plant tissues. Dew provides this water, creating conditions favorable for disease development. The duration of leaf wetness, determined by when dew forms and how long it persists, is a key factor in disease forecasting models. Farmers use these models to time fungicide applications and other management practices, reducing disease pressure while minimizing chemical use. The formation of dew on soil surfaces affects the moisture available to seeds and shallow-rooted plants. In some ecosystems, particularly in arid and semi-arid regions, dew penetration into the soil surface can support germination and early growth even in the absence of rainfall. The amount of moisture that penetrates depends on the soil texture, structure, and surface properties. Sandy soils with large pore spaces allow deeper penetration, while fine-textured soils, or those with surface crusts, may absorb less dew. The measurement of dew has evolved from simple observation to sophisticated instrumentation. Early methods involved weighing absorbent materials before and after dew formation to quantify the amount of water deposited. Modern techniques use electronic sensors that detect changes in electrical properties, optical sensors that measure surface wetness, or micrometeorological methods that calculate dew formation from energy balance equations. Each method has advantages and limitations, and researchers often use multiple approaches to validate their measurements. The role of dew in urban environments differs from its role in natural ecosystems. Cities, with their abundance of artificial surfaces, modified microclimates, and altered humidity patterns, create unique conditions for dew formation. Some surfaces, like metal and glass, cool rapidly and collect dew readily. Others, like concrete and asphalt, retain heat and may remain above the dew point even when surrounding areas are wet. The urban heat island effect reduces dew formation in city centers compared to surrounding rural areas, altering the moisture dynamics of these environments. The chemical composition of dew reflects both the atmosphere from which it condenses and the surface on which it forms. Dew can dissolve gases from the air, capture aerosol particles, and leach substances from the surface beneath it. Analysis of dew chemistry provides information about air quality, atmospheric deposition, and surface contamination. In polluted areas, dew could be quite acidic, with pH values similar to acid rain. In clean environments, it more closely resembles distilled water, though it still contains dissolved gases and trace minerals. The formation of dew on vehicle surfaces is a familiar experience for many people. Cars parked outdoors overnight often develop a coating of dew, particularly on horizontal surfaces like roofs and hoods. The metal and glass surfaces of vehicles cool efficiently through radiative heat loss, and their smooth surfaces allow dew to form in visible sheets rather than individual droplets. The patterns of dew formation can reveal airflow around the vehicle, with areas of turbulence or sheltering showing different amounts of moisture. The relationship between dew and air quality monitoring has become an area of research interest. Because dew captures atmospheric particles and dissolves gases, analyzing its composition can provide information about air pollution levels and sources. Dew collectors, simple devices that mimic natural dew formation on artificial surfaces, can be deployed to sample atmospheric deposition in areas where more sophisticated monitoring equipment is not available. The technique is particularly useful in remote or resource-limited settings. The formation of dew on electronic equipment can cause problems, particularly in humid environments or when equipment is moved from cool to warm locations. Condensation on circuit boards, connectors, and other components can lead to short circuits, corrosion, and equipment failure. Engineers design electronics with protective coatings, sealed enclosures, and sometimes small heaters to prevent condensation in critical areas. Understanding the conditions that lead to dew formation helps in designing equipment that can operate reliably in diverse environments. The study of dew in forensic science has occasional applications. The presence or absence of dew on objects at a crime scene can provide information about timing and conditions. An object that was moved or placed after dew formation would lack the moisture present on undisturbed surfaces. While not a primary forensic technique, such observations can contribute to the overall analysis of a scene, adding another piece to the puzzle of reconstructing events. The formation of dew on telescope mirrors and lenses is a concern for astronomers. Optical surfaces that cool below the dew point develop a coating of moisture that scatters light and degrades image quality. Astronomers use dew shields, heaters, and careful site selection to minimize this problem. Observatory sites are often chosen in part for their low humidity and stable atmospheric conditions, which reduce the risk of dew formation during critical observation periods. The interaction between dew and solar panels affects their performance in the early morning hours. A coating of dew on a solar panel surface can scatter and absorb incoming light, reducing the amount of energy reaching the photovoltaic cells. However, dew also helps clean the panel surface, washing away dust and other contaminants that accumulate over time. The net effect depends on the local climate, the frequency of dew formation, and the amount of dust in the environment. The formation of dew on aircraft surfaces is monitored carefully in aviation. While dew itself is not a major hazard, the conditions that produce it, particularly high humidity and cooling temperatures, can also lead to fog formation or, if temperatures drop further, to ice formation. Pilots and ground crews watch for dew as an indicator of atmospheric conditions, using it as one of many signs to assess weather and flight safety. The role of dew in seed dispersal is subtle but present in some plant species. Seeds with mucilaginous coatings can absorb dew, causing them to swell and potentially changing their position or attachment to the parent plant. In some cases, this moisture-driven movement aids in dispersal, helping seeds separate from the parent plant or move across the ground surface. The process is slow and incremental, but over time it contributes to the spatial distribution of plant populations. The formation of dew on historical monuments and buildings is a factor in their preservation. Repeated cycles of wetting and drying can contribute to the deterioration of stone, mortar, and other building materials. Moisture from dew can dissolve salts within the material, which then crystallize as the surface dries, creating pressure that fractures the stone. Conservators study dew patterns on historic structures to understand deterioration processes and develop strategies to protect these irreplaceable artifacts. The relationship between dew and human comfort is indirect but real. High humidity levels that favor dew formation can make the air feel heavy and uncomfortable, even at moderate temperatures. The presence of dew in the morning indicates that humidity levels were high overnight, which can affect sleep quality and how refreshed people feel upon waking. In hot, humid climates, the persistence of high humidity day and night, marked by abundant dew formation, contributes to the overall sensation of oppressive weather. The formation of dew on camping equipment is a familiar experience for outdoor enthusiasts. Tents, sleeping bags, and other gear develop coatings of moisture overnight, particularly in humid environments or near bodies of water. Campers learn to anticipate this, setting up shelters to promote air circulation, choosing campsites away from low-lying areas where humidity is highest, and allowing time in the morning for gear to dry before packing. The presence of dew is part of the rhythm of outdoor living, a reminder of the constant exchange between atmosphere and surface. The study of dew in climate models helps researchers understand regional and global water cycles. While dew represents a small fraction of total precipitation in most locations, it is still part of the overall movement of water through the Earth system. Models that accurately represent dew formation and evaporation provide more realistic simulations of surface energy balance, soil moisture, and vegetation water stress. Improving these representations enhances our ability to predict climate and weather patterns. The formation of dew on power lines and electrical infrastructure can occasionally cause problems. While dew itself is not highly conductive, it can accumulate pollutants from the air that increase its conductivity, potentially leading to leakage currents or tracking on insulator surfaces. Utility companies design electrical systems to handle these conditions, using insulators with shapes that shed water quickly and materials that resist contamination buildup. The relationship between dew and traditional weather forecasting has deep roots. Before modern meteorology, people relied on observations of natural phenomena to predict weather. Heavy dew on a clear night often indicated stable atmospheric conditions and a low likelihood of rain in the immediate future. The absence of dew on a humid night might suggest increasing wind or cloud cover, signs of changing weather. These traditional indicators based on centuries of observation, often aligned with the physical processes that meteorologists now understand through scientific study. The formation of dew on musical instruments affects their tuning and playability. Wooden instruments, particularly those used outdoors or in humid environments, can absorb moisture from dew, causing the wood to swell and affecting the instrument's tone and intonation. Musicians who perform outdoors in the early morning or evening, when dew is likely, take precautions to protect their instruments, using cases, covers, and climate control when possible. The role of dew in traditional medicine and folk remedies appears in many cultures. Dew collected from certain plants was believed to have healing properties, and elaborate rituals sometimes surrounded its collection. While modern science does not support most of these traditional claims, the practices reflect a deep attention to natural cycles in an attempt to harness the perceived purity and freshness of dew for human benefit. The formation of dew on food crops affects harvest timing and post-harvest handling. Crops harvested while still wet with dew are more susceptible to damage, disease, and quality loss during storage. Farmers often wait for dew to evaporate before beginning harvest operations, particularly for crops like grains and hay that must be stored at low moisture levels. This waiting period, determined by the rate of dew evaporation, influences the daily rhythm of agricultural work during harvest season. The study of dew in ecology extends to its role in nutrient cycling. Dew can leach nutrients from plant surfaces, including minerals deposited from dust and compounds exuded by the plant itself. These nutrients then drip to the soil surface or are absorbed by other organisms, contributing to the complex web of nutrient flows within an ecosystem. While the amounts involved are small compared to other nutrient pathways, they are part of the overall balance that sustains ecosystem function. The formation of dew on synthetic materials reveals the diversity of surface properties in modern environments. Plastics, treated fabrics, and composite materials each interact with water vapor in different ways, some encouraging dew formation and others resisting it. The development of superhydrophobic surfaces, inspired by natural examples like lotus leaves, creates materials that shed dew almost instantly, finding applications in everything from outdoor clothing to industrial equipment. The relationship between dew and ground-level ozone formation is complex. While dew itself does not produce ozone, the moisture it provides can affect the chemical reactions that occur on plant and soil surfaces. Some of these reactions involve volatile organic compounds and nitrogen oxides, precursors to ozone formation. Understanding these interactions helps atmospheric scientists model air quality and develop strategies to reduce pollution. The formation of dew in greenhouses and controlled environment agriculture requires management to prevent disease while maintaining optimal humidity for plant growth. Growers use ventilation, heating, and sometimes dehumidification to control the greenhouse climate, reducing dew formation on plant surfaces during critical periods. Balancing these factors requires understanding both plant physiology and the physics of condensation, integrating knowledge from multiple disciplines. The role of dew in fire ecology is subtle but present. In fire-prone ecosystems, dew provides brief periods of elevated fuel moisture, particularly in the early morning hours. This moisture can reduce fire intensity and spread rate during these periods, though the effect is temporary as the sun quickly evaporates the dew. Fire managers account for these diurnal moisture cycles when planning prescribed burns and assessing wildfire behavior. The formation of dew on animal fur and feathers affects insulation and waterproofing. Many animals have evolved surface structures and behaviors that shed dew quickly, maintaining the insulating properties of their coats. Birds preen their feathers to distribute oils that enhance water repellency, and many mammals have guard hairs that protect the insulating undercoat from moisture. These adaptations reflect the evolutionary pressure to maintain body temperature regulation in environments where dew forms regularly. The study of dew in archaeology has revealed information about past climates and human activities. Analysis of ancient surfaces, including pottery, stone tools, and building materials, can sometimes detect patterns of moisture exposure that indicate dew formation. These patterns, combined with other evidence, help researchers reconstruct the environmental conditions experienced by past societies and understand how people adapted to their climates. The formation of dew on roads and pathways affects safety, particularly on bridges and overpasses that cool more rapidly than surrounding surfaces. The thin layer of moisture can reduce traction, and in marginal temperatures, dew can freeze into a nearly invisible coating of ice known as black ice. Transportation authorities monitor conditions that favor dew formation, particularly in the hours before dawn when temperatures are lowest and dew is most likely. The relationship between dew and sleep quality has been explored in studies of bedroom environment. High humidity levels that favor dew formation outdoors often indicate humid indoor conditions as well, which can affect comfort and sleep. While people do not directly experience dew formation in their bedrooms, the atmospheric conditions that produce are part of the overall environmental factors that influence rest and recovery. The formation of dew on scientific instruments and field research requires careful consideration. Sensors, data loggers, and other equipment deployed outdoors must either be protected from dew or designed to function reliably when wet. Researchers use shelters, heating elements, and water-resistant designs to ensure data quality. Understanding when and how dew forms helps in planning field campaigns and interpreting measurements. The role of dew in traditional agriculture extends beyond simple moisture provision. In some farming systems, the presence or absence of dew serve as a guide for planting times, irrigation scheduling, and harvest decisions. Farmers developed detailed knowledge of local dew patterns, understanding which fields collected more moisture, which crops benefited most, and how to interact with other weather phenomena. This traditional knowledge, accumulated over generations, represented a sophisticated understanding of local microclimates. The formation of dew on memorial stones and grave markers is part of the natural weathering these objects experience. The repeated cycles of wetting and drying gradually alter the stone surface, softening inscriptions and changing the appearance of the material. For those who tend these sites, the presence of dew in the morning is a reminder of the constant, gentle processes that connect past and present, a physical manifestation of time's passage. The study of dew and art conservation addresses the risks moisture poses to paintings, sculptures, and other artworks. Museums and galleries carefully control temperature and humidity to prevent condensation on cold surfaces, which could damage delicate materials. Understanding the dew point and maintaining conditions above it protects collections from moisture-related deterioration, preserving these works for future generations. The formation of dew on playground equipment and outdoor recreational facilities requires consideration for safety and maintenance. Metal slides, swings, and climbing structures develop dew overnight, creating slippery surfaces in the early morning. Parks departments and facility managers account for this in their maintenance schedules and sometimes post warnings during seasons when dew is most prevalent. The relationship between dew and traditional time keeping appears in some cultures, where the formation and evaporation of dew mark the passage of night into day. Before mechanical clocks, people relied on natural phenomena to structure their daily activities, and dew served as one of many indicators of the time and the appropriate activities for different parts of the day. The formation of dew on memorial gardens and contemplative spaces adds to their atmosphere of quietness and renewal. The moisture that appears with dawn and vanishes by mid-morning echoes themes of transience and cyclical return that often characterize these spaces. For visitors, the presence of dew can enhance the sense of freshness and new beginning that such places are designed to evoke. The study of dew and landscape architecture informs plant selection and site design. Designers consider which areas of a property will collect more dew based on exposure, surface materials, and vegetation patterns. This knowledge influences choices about where to place moisture-sensitive plants, how to grade surfaces for drainage, and how to create microclimates that support diverse plantings. The formation of dew on observation equipment used by naturalists and wildlife watchers affects fieldwork. Binoculars, camera lenses, and spotting scopes can develop dew on their optical surfaces, particularly during early morning observation sessions. Experienced observers anticipate this, using lens hoods, protective covers, and sometimes gentle heating to maintain clear views during prime wildlife activity periods. The relationship between dew and circadian rhythms in plants is an area of ongoing research. Some plants respond to the presence of moisture on their leaves, adjusting stomatal opening or other physiological processes. The regular cycle of dew formation and evaporation provides a reliable environmental signal that plants may use, along with light and temperature, to coordinate their daily rhythms. The formation of dew on memorial benches and outdoor seating areas is a practical consideration for public spaces. Designers select materials and finishes that shed water quickly, ensuring that seating is usable soon after dawn. The choice of wood, metal, or composite materials affects how much dew accumulates and how quickly it evaporates, balancing aesthetics with functionality. The study of dew in ethnobotany reveals how different cultures incorporated observations of dew into their plant knowledge. Some traditional practices involve collecting plants at specific times relative to dew formation, believing that the moisture affected the plant's properties. While modern science may not validate all these beliefs, they reflect careful observation of plant-environment interactions and the integration of natural cycles into cultural practices. The formation of dew on outdoor lighting fixtures can affect their performance and longevity. Moisture that condenses inside or on the surface of lights can reduce illumination, cause electrical problems, or promote corrosion. Manufacturers design outdoor lighting with seals, drainage, and materials that resist moisture damage, applying principles of dew formation to create more durable products. The relationship between dew and thermal comfort in outdoor spaces influences landscape design and urban planning. Areas that collect heavy dew often feel more humid and less comfortable in the early morning. Designers can modify these conditions through plant selection, surface materials, and site grading, creating spaces that are pleasant to use throughout the day. The formation of dew on commemorative plaques and outdoor signage gradually affects their legibility. The repeated wetting and drying cycles contribute to weathering, fading, and corrosion. Selecting appropriate materials and finishes, based on understanding of local dew patterns, helps ensure that these markers remain readable for their intended lifespan. The study of dew in environmental education provides an accessible entry point for learning about atmospheric science, thermodynamics, and ecology. Observing dew formation requires no special equipment, just attention and curiosity. Teachers and educators use dew as a tangible phenomenon that connects abstract scientific concepts to everyday experience, helping students develop scientific thinking through direct observation. The formation of dew on surfaces of different colors reveals the relationship between surface properties and radiative cooling. Darker surfaces absorb more solar radiation during the day, storing more heat, which can delay or reduce dew formation at night. Lighter surfaces reflect more sunlight and cool more readily, often collecting more dew. This relationship between color, temperature, and moisture has practical applications in building design, agriculture, and material science. The gentle accumulation of dew continues through these quiet hours, each droplet a small achievement of physics and chemistry. Each surface a stage for this molecular performance. The process asks nothing of us, requires no attention, proceeds with or without witnesses. Yet in its reliability, its quiet constancy, it offers a kind of comfort. The world continues its cycles. Water moves through its phases, and morning arrives dressed in these tiny spheres of moisture, catching the first light, holding it briefly, then releasing it as they evaporate into the warming air. The patterns of dew across a landscape create a temporary map of microclimates, a visible record of temperature, humidity, and surface properties. This map changes with the seasons, with weather patterns, with the growth and senescence of vegetation. Reading this map, understanding what it reveals about the environment, connects us to the physical processes that shape the world around us. The study of dew, pursued across centuries and cultures, reflects our enduring curiosity about natural phenomena. From ancient observations to modern scientific investigations, people have watched dew form, wondered about its origins, and sought to understand its role in the larger systems of atmosphere and ecosystem. This continuity of inquiry, this thread of curiosity running through human history, is itself a kind of constancy, as reliable as the dew itself. The formation of each droplet, invisible in its beginning, gradually becoming substantial enough to catch light and attention, mirrors many processes of growth and accumulation. Small additions, repeated over time, create visible results. This principle, demonstrated in the formation of dew, applies across scales and contexts, a reminder that significant changes often emerge from countless small increments. As we consider these many facets of dew formation, the physics and chemistry, the ecological roles and cultural meanings, the practical implications and aesthetic qualities, a picture emerges of a phenomenon both simple and complex. Simple in its basic mechanism, the condensation of water vapor on a cool surface, yet complex in its variations, its interactions, its effects across different systems and scales. The moisture that appears with dawn and vanishes by mid-morning participates in cycles that span from molecular to global scales. Each droplet contains water molecules that have cycled through the atmosphere countless times, that have been part of oceans and rivers, clouds and rain, plants and animals. The dew on a grass blade connects to the vast circulation of water through the Earth system, a local manifestation of planetary scale processes. In the quietness of this knowledge, in the calm understanding of these processes, there is space for rest. The world continues its patterns, reliable and constant, asking nothing but offering these small wonders for those who pause to notice. The dew will form again tomorrow night, and the night after, following the same principles, responding to the same forces, creating the same gentle transformation of surfaces from dry to glistening. Your breathing is perhaps slowed as we've moved through these ideas together. Your mind may feel the pleasant weight of information gently accumulated, like dew itself, each fact a small droplet adding to the whole. There is no urgency here, no need to retain every detail. The knowledge is available, like the dew, appearing when conditions are right, present for those who seek it. If you find yourself still awake, still following these words, know that there are more such journeys available, more quiet explorations of the natural world and the principles that govern it. Each topic offers its own particular calm, its own pathway into rest through understanding. But if sleep is approaching, you can let these words fade. Let the images of dew-covered surfaces blur and soften. Let the concepts settle into the background of consciousness. The dew will form tonight, wherever you are, if conditions allow. It will appear without announcement, accumulate in silence, and catch tomorrow's early light. This process continues, has always continued, will continue long after this moment has passed. In that continuity, that reliable repetition, there is something deeply restful. The world knows what to do. The water vapor knows when to condense. The surfaces know how to cool. Everything proceeds according to principles as old as the atmosphere itself. You are part of this same world, subject to the same physical laws, connected to the same cycles. Your body knows how to rest, how to release the day's tensions, how to move through the stages of sleep. Like dew formation, this process proceeds best when conditions are right, when a mind is quiet and the body is still, when the environment supports rather than disrupts. As we reach the end of this exploration, the facts and details may already be blurring together, becoming less distinct, like dew droplets coalescing into larger drops that lose their individual identity. This is natural and expected. The purpose was not to memorize, but to experience, to move gently through ideas, to allow the mind to engage with something calm and structured while the body prepared for rest. The morning will come, as it always does, and if you look, you may see dew on the grass, on leaves, on surfaces that cooled through the night. You'll understand now, at least in outline, how it came to be there, the invisible processes that created these visible results. And in that understanding, there may be a small pleasure, a quiet satisfaction in recognizing the principles at work. But for now, in this moment, the only task is rest. The dew will form or not form. The world will continue its cycles, and you can release your attention, let go of focus, allow sleep to approach at its own pace. There is nothing more required, nothing left to understand, nothing that cannot wait for another day. The gentle rhythm of dew formation, the quiet accumulation of moisture, the patient work of condensation, all continue in the background of the world, a soft constant that requires no witness. And in the same way, your own rest can proceed, natural and unforced, following its own rhythms, moving through its own cycles. If these words have brought some measure of calm, some easing of the day's tensions, then they have served their purpose. If sleep is near, you can welcome it. If wakefulness persists, you can rest in the knowledge that more such journeys exist, more quiet paths through scientific understanding, more opportunities to let the mind engage gently while the body settles. The dew knows nothing of worry, nothing of urgency. It forms when conditions allow, following principles that need no intention or effort. In the same way, rest comes when the conditions are right, when the mind releases its grip on the day's concerns, when the body finds its comfortable position and settles into stillness. We've traveled together through the science of dew formation, from the basic physics of condensation to the subtle interactions with ecosystems and culture. The journey has been gentle, paced for calm rather than excitement, designed to inform while soothing. As it ends, you can let it go, release the details, keep only the sense of having spent time with something peaceful and true. The night continues, wherever you are, moving toward dawn at its own steady pace. The temperature falls or holds steady. The humidity persists or changes. The surfaces cool and perhaps collect their coating of moisture. These processes proceed without attention, without effort, following the laws that govern matter and energy. And you, too, can proceed without effort, allowing the natural processes of rest to unfold. The body knows what to do. The mind knows how to quiet. The transition into sleep, like the formation of dew, happens best when we simply allow it, when we create the right conditions and then step back, trusting the process to complete itself. In this trust, in this release, there is deep rest available. The world continues, reliable and constant. The cycles persist, the patterns repeat, and within these larger rhythms, your own rest is held, supported, made possible by the same fundamental principles that govern everything from the smallest dew droplet to the largest atmospheric system. So rest now if you can. Let go if you're able. The exploration is complete. The journey through these facts and ideas has reached its natural end. What remains is simply the quiet of the night, the comfort of your resting place, and the gentle approach of sleep, patient, and inevitable as the dew itself.